Imagine standing at the edge of an abyss, a place of such profound emptiness that it seems to contain nothing at all. No light, no sound, no matter, not even the familiar framework of space and time. It is from this perfect void, from this conceptual nothingness, that everything that has ever existed and everything that will ever exist is thought to have exploded into being. Have you ever stood under a clear night sky, looked up at the scattered diamonds of distant stars, and felt the weight of that question, why is there something, when there could have been nothing at all? How is it possible that from this sheer, featureless emptiness, the entire tapestry of the cosmos, the galaxies, the stars, the planets, and eventually, the very consciousness that is asking this question was born? These are not idle philosophical musings. They are the central, driving questions of modern cosmology, and they lead us to a truth that is far stranger and more profound than any of our ancient myths. At the deepest, most fundamental level of reality, in the bizarre and beautiful realm of quantum mechanics, we have discovered that true emptiness does not exist. What we perceive as the void is, in fact, a turbulent, seething ocean of energy and potential, a place where something is constantly happening. It is a cosmic womb, a generative silence, a nothing that contains the seeds of everything. For millennia, human cultures have grappled with the concept of the void, attempting to capture its essence through myth, philosophy, and art. The ancient Greeks spoke of chaos, the formless, primordial abyss from which the first gods and the ordered cosmos emerged. In the rich tapestry of Hindu thought, we find the concept of shunyata, an emptiness that is not a nihilistic void, but a state of pure, unmanifest potential, a dynamic emptiness that is the source of all phenomena. The Tao Te Ching, one of the foundational texts of Taoism, begins with a meditation on the Wu, the nameless, formless void that is, paradoxically, the mother of the 10,000 things, the entirety of the manifest world. It is a remarkable testament to the power of human intuition that these ancient contemplative traditions arrived at a vision of emptiness that resonates so deeply with the discoveries of 21st century physics. Our most advanced scientific theories, expressed in the rigorous language of mathematics, are now telling us a story that our ancestors seem to know in their bones, that the void is not an absence, but a presence, not an end, but a beginning. Quantum mechanics, that strange and wonderful pillar of modern science, reveals that even in a perfect vacuum, a space cooled to absolute zero and shielded from all external influences, there is an incessant, irreducible quantum jiggle. This is the world of quantum fluctuations, a place where pairs of virtual particles and their antimatter counterparts are constantly bubbling into existence, borrowing a tiny amount of energy from the vacuum for an immeasurably short time before annihilating each other and returning their borrowed energy to the void. This is not a theoretical fantasy. It is a direct consequence of one of the most fundamental principles of nature. Werner Heisenberg's uncertainty principle. Formulated in 1927, this principle states that there is an irreducible trade-off in our knowledge of certain pairs of properties of a quantum system. The more accurately you know a particle's position, the less accurately you can know its momentum, and vice versa. This fundamental uncertainty extends to energy and time. For a very short period of time, the energy of a system can be uncertain, allowing for these spontaneous, fleeting creations of matter and antimatter from the nothingness of the vacuum. This means that at the most fundamental level, there is no such thing as a truly empty or static space. Every point in the cosmos is permeated by a web of quantum fields, one for each type of fundamental particle. These fields are never completely at rest. They are always vibrating, always fluctuating, even in their lowest energy state. This irreducible minimum energy of the vacuum is known as zero-point energy. It is the baseline hum of the universe, the silent, ever-present music of the void. And this is not just a mathematical abstraction. The physical effects of these virtual particles and their zero-point energy can be measured. The Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948, and later confirmed experimentally, shows that two uncharged parallel metal plates placed very close together in a vacuum will be pushed together by an invisible force. This force is not gravity, nor electromagnetism. It is the pressure of the quantum vacuum itself. The space between the plates can only accommodate virtual particles of certain wavelengths, while the space outside the plates can accommodate all wavelengths. This creates a pressure differential, a net force pushing the plates together. The void itself can exert a physical force. It is a stunning, tangible demonstration that what we call emptiness is, in fact, a dynamic, energetic, and powerful medium. The creative potential of this quantum vacuum is not limited to the fleeting dance of virtual particles. It may be the very source of our entire universe. The theory of cosmic inflation, one of the cornerstones of modern cosmology, proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated, exponential expansion. The driving force behind this inflation is thought to have been the energy of a quantum field, known as the inflaton field, trapped in a high-energy, false vacuum state. As this field relaxed to its true lower energy state, it released its stored energy, flooding the nascent universe with the matter and radiation we see today. In this picture, the universe is a kind of macroscopic quantum fluctuation, a bubble of reality that was inflated to cosmic proportions by the energy of the void. This idea leads to an even more mind-boggling possibility, the quantum foam, first envisioned by the physicist John Wheeler. This is the idea that at the smallest possible scales of distance, the so-called Planck length, an unimaginably small 10 to the power of minus 35 meters, the very fabric of space-time is not smooth and continuous, but a chaotic, turbulent foam of microscopic black holes and wormholes, constantly being created and annihilated by quantum fluctuations. At this fundamental level, our familiar notions of space and time break down. This is the realm of quantum gravity, the yet-to-be-discovered theory that will unify Einstein's general relativity with quantum mechanics. In this foamy, quantum reality, a sufficiently large fluctuation could, in principle, give rise to a new, expanding universe. Our cosmos could be a single, fortunate bubble that emerged from this infinite, eternal sea of quantum potential. This is the scientific version of a universe from nothing, a concept explored by physicist Lawrence Krauss. The nothing in this context is not an absolute philosophical void, but the rich, dynamic, and endlessly creative quantum vacuum. This completely inverts our classical understanding of reality. We no longer see the void as a passive, empty stage upon which the cosmic drama unfolds. We see the void itself as the primary actor, the generative source, the mother of all that is. The emptiness between the stars is not an absence. It is the presence of an infinite potential, a potential that, some 13.8 billion years ago, blossomed into the vast, complex, and beautiful universe we call home. And so, as you lie in the quiet of the night, as your consciousness begins to drift into the silent, inner space of sleep, you are, in a sense, returning to this primordial state. You are entering your own personal quantum vacuum, a space of pure potential, a space where new thoughts, new dreams, and new realities can be born from the creative silence of your own being. In the early 1980s, the standard Big Bang model, while remarkably successful in describing the evolution of the universe from a hot, dense state, was facing a series of deep conceptual puzzles. It was like having a perfectly working car, but with no idea how the engine was built or why it had started in the first place. Then, on a cold December night, in 1979, a young American physicist named Alan Guth, poring over his equations, had what he later called a spectacular realization. He had stumbled upon the cosmic ignition key, the theory he conceived that night, the theory of cosmic inflation, would not just solve the lingering puzzles of the Big Bang, it would fundamentally reshape our understanding of the first infinitesimal moments of creation, and it would do so by unleashing the immense creative power of the quantum vacuum. The story that inflation tells is a dramatic one. It proposes that in the very first flicker of time, between roughly 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang, the universe underwent a period of astonishing, hyper-accelerated, exponential expansion. It was a cosmic growth spurt of truly epic proportions. During this fleeting, almost timeless instant, the size of the universe increased by a factor of at least 10 to the power of 26, a number so large it is difficult to represent with analogies. It is like taking an object smaller than a single proton and stretching it to the size of a grapefruit in a time far shorter than it takes light to cross that same proton. This is not just an expansion in space, it is an expansion of space itself, a stretching of the very fabric of reality at a rate that completely dwarfs the speed of light. The engine that powered this explosive growth, according to inflationary theory, was the energy of a quantum field, dubbed the inflaton field, which was momentarily trapped in a high-energy, unstable state known as a false vacuum. Imagine a ball perched precariously in a small divot at the very peak of a vast, steep hill. It possesses a huge amount of potential energy, and it is in a state of metastable equilibrium. A tiny quantum jiggle is all it would take to send it cascading down the hill, releasing its stored potential energy as the kinetic energy of motion. The false vacuum of the early universe was like this ball at the top of the hill. It was a state of incredibly high and uniform energy density, and this energy had a peculiar and powerful property. It exerted a strong negative pressure, which, according to Einstein's theory of general relativity, creates a powerful gravitational repulsion. It was this anti-gravity of the false vacuum that drove the exponential inflationary expansion. Eventually, this false vacuum state decayed, like the ball rolling down the hill, into the true lower energy vacuum state of our current universe. This process, called reheating, was a cataclysmic event. The immense energy that had been stored in the inflaton field was released, flooding the now vast, empty universe with a hot, dense, and uniform soup of fundamental particles and radiation. This is the starting point of the standard hot Big Bang model. Inflation, in this sense, is not an alternative to the Big Bang. It is a prequel, a brilliant and necessary prologue that sets the stage and explains the seemingly miraculous initial conditions from which the rest of cosmic history unfolded. The true elegance of inflationary theory lies not just in its dramatic narrative, but in its remarkable ability to solve the deep conceptual puzzles that had plagued the standard Big Bang model. One of the most profound of these was the horizon problem. When we observe the cosmic microwave background CMB, the faint, relic radiation from the infant universe, we find that it has an almost perfectly uniform temperature in all directions, to an accuracy of about 1 part in 100,000. This is a profound mystery. In the standard Big Bang model without inflation, regions of the sky that are on opposite horizons today were never in causal contact with each other. They were too far apart for light or any other signal to have traveled between them in the time since the beginning of the universe. So how could they have possibly reached the same temperature? It is as if you walked into a vast, cavernous room and found that the temperature at every single point was identical to within a tiny fraction of a degree, without any heating or cooling system to have ever been turned on. Inflation provides a beautifully simple solution. Before the period of exponential expansion, the region of space that would eventually become our entire observable universe was an incredibly tiny subatomic patch. It was so small that it was in perfect causal contact with itself. There was plenty of time for all parts of this patch to interact, to exchange energy, and to reach a state of thermal equilibrium, a state of uniform temperature. Inflation then took this tiny, smooth patch and stretched it to astronomical proportions in the blink of an eye. The uniformity was preserved, locked into the expanding fabric of space, creating the smooth, isotropic universe we see today. The second major puzzle solved by inflation is the flatness problem. According to general relativity, the geometry of spacetime is determined by its total density of matter and energy. If this density is above a certain critical value, the universe will be closed, like the surface of a sphere, and will eventually collapse. If it is below the critical value, the universe will be open, like the surface of a saddle, and will expand forever. The flat universe of Euclidean geometry is a special knife-edge case, corresponding to a density that is exactly equal to the critical density. And our observations tell us that our universe is astonishingly, exquisitely flat. For this to be the case, the initial density of the universe at the time of the Big Bang would have had to be fine-tuned to a degree of precision that is almost beyond comprehension, about 1 part in 10 to the power of 60. This seems like an absurdly improbable coincidence. Inflation solves this problem in a natural and elegant way. Any initial curvature that the universe may have had, whether positive or negative, would have been stretched out and flattened by the immense exponential expansion, in the same way that inflating a small, wrinkled balloon to the size of the Earth would make its surface appear perfectly flat to an observer on it. Inflation drives the geometry of the universe so close to perfect flatness that it is, for all practical purposes, indistinguishable from it. But inflation does more than just solve old problems. It makes a remarkable and testable prediction. The theory states that the tiny, unavoidable quantum fluctuations in the inflaton field itself during the period of inflation would not have been smoothed out. Instead, they would have been stretched to macroscopic and even astronomical scales. These stretched in time quantum fluctuations would have become the seeds of cosmic structure, the tiny variations in density that, over billions of years, would grow under the influence of gravity to become all the galaxies, the clusters of galaxies, and the vast cosmic web that we see today. The specific statistical properties of these primordial fluctuations, they're near, but not perfect. Scale invariants are a unique fingerprint of inflation, and they have been confirmed with stunning precision by our detailed maps of the cosmic microwave background. We are, in the most literal and profound sense, the children of quantum fluctuations. Our entire cosmic home, with all its grandeur and complexity, is a macroscopic fossil of the inherent uncertainty of the primordial quantum void. A void that was momentarily supercharged with an incredible inflationary energy, the theory of inflation. In its more modern and sophisticated forms, has led to a concept that is even more profound and mind-altering than the Big Bang itself, the idea of eternal inflation and the multiverse. The Russian-American cosmologist Andrei Linder, one of the key architects of modern inflationary theory, realized that the process of inflation, once started, may be very difficult to stop. In his model of chaotic inflation, the inflaton field is not a single, uniform entity, but a field that has different, random values in different regions of the primordial universe. In some regions, the field will quickly roll down its potential hill. Inflation will end, and a bubble universe like ours will be born in a hot Big Bang. But in other regions, quantum fluctuations can kick the field up the hill, causing inflation to continue, and even to become a self-reproducing eternal process. In this scenario, the end of inflation in our region was just a local event. The larger meta-universe, the inflationary sea, is still out there, expanding at an incredible rate and constantly spawning new bubble universes. The Big Bang was not a singular, unique event in the history of time. It is a common, ongoing process in the vast, eternal landscape of the multiverse. This is a vision of reality that is almost impossible to fully comprehend. Our entire observable universe, with its hundreds of billions of galaxies, is just one bubble in an infinite, bubbling foam of other universes. And these other universes may not be like our own. The decay of the inflaton field in each bubble could lead to different vacuum states, resulting in different fundamental particles, different forces of nature, different physical laws. There could be universes with 2 dimensions of space, or 10. Universes where gravity is a repulsive force, or where the speed of light is different. Most of these universes would be sterile, bizarre, and inhospitable wastelands, incapable of supporting any form of complexity or life. But in an infinite multiverse, even the most improbable events become not just possible, but inevitable. The existence of a universe like ours, with its specific and seemingly fine-tuned set of physical constants that allow for the formation of stars, planets, and conscious observers, is no longer a miracle to be explained. It becomes a simple selection effect. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves living on a planet with liquid water and a breathable atmosphere we could not exist to ask the question in any of the other, far more numerous, inhospitable environments. The multiverse, in this sense, provides a scientific, albeit untestable, explanation for the anthropic principle. The idea of eternal inflation and the multiverse is on the cutting edge of theoretical physics, and it is by no means universally accepted. Critics point out that it is, by its very nature, unobservable, and therefore may not be a truly scientific theory. But its proponents argue that it is a natural and almost unavoidable consequence of combining our best theories of cosmology and quantum field theory. And there may be ways to search for indirect, circumstantial evidence. If our bubble universe had, in its distant past, collided with another bubble, it might have left a bruise on our cosmos, a specific, circular pattern of temperature fluctuations in the cosmic microwave background. The search for such a cosmic scar is an active, if long-shot, area of research. Whether the multiverse is a physical reality or a beautiful mathematical dream, the theory of inflation has fundamentally and irrevocably changed our view of our own origins. It has taken the Big Bang from a mysterious, unexplained singularity and placed it within a larger, dynamic, and potentially eternal cosmic context. It has shown us how the grand, macroscopic structure of our universe can be born from the subtle, microscopic quantum fluctuations of the void. And it has opened our minds to the breathtaking possibility that our entire cosmos is just a single, fleeting note in an infinite and eternal cosmic symphony. The concept of the Big Bang itself, the central event in our cosmic story, is one that is often shrouded in misconception. The popular image is that of a gigantic firework, a singular explosion happening at a specific point in a pre-existing empty space. But this picture is fundamentally wrong. The Big Bang was not an explosion in space. It was an explosion of space. It was not an event that happened at a particular location. It was an event that happened everywhere at once. To grasp this counterintuitive idea, the analogy of an expanding balloon is helpful. If you imagine our three-dimensional space as the two-dimensional surface of a balloon, and you draw a number of dots on this surface to represent galaxies, then, as you inflate the balloon, you will see that every dot is moving away from every other dot. An observer on any given dot would see all the other dots receding from them, and the further away a dot is, the faster it would appear to be moving away. There is no center to this expansion on the surface of the balloon. The expansion is happening everywhere. The fabric of the balloon itself is stretching. In the same way, the expansion of the universe is a stretching of the fabric of space-time. Every point in our current universe, including the point where you are right now, was part of that initial, infinitely hot and dense state. The Big Bang happened right here, and everywhere else. This is a direct consequence of Einstein's general theory of relativity, which describes space and time not as a static, absolute background, but as a dynamic, physical entity that can be bent, warped, and stretched by the presence of matter and energy. The Big Bang, then, is not a theory of the origin of the universe from nothing. It is a theory of the evolution of the universe from a very hot, dense, and rapidly expanding initial state. It does not, in its standard form, address the question of what caused the Big Bang, or what, if anything, came before it. Those are questions that lie beyond the domain of the theory, in the realm of quantum gravity and the speculative cosmologies we have discussed. The story that the Big Bang does tell is the story of the first 14 billion years of our universe's life. A story of cooling, of expansion, and of the gradual emergence of complexity from a state of primordial simplicity. In the first fractions of a second, The universe was an unimaginably hot and dense soup of fundamental particles, quarks, leptons, and the force-carrying bosons, a state known as a quark-gluon plasma. As the universe expanded and cooled, this plasma froze out. After about 1 microsecond, the quarks bound together to form the protons and neutrons that make up the nuclei of atoms for the next few minutes. In a process known as Big Bang nucleosynthesis, these protons and neutrons fuse together to form the nuclei of the lightest elements, mostly hydrogen and helium, with trace amounts of lithium. The universe was still a hot, dense, and opaque plasma. The temperature was so high that electrons were not bound to the atomic nuclei. This sea of free electrons acted like a dense fog, constantly scattering photons of light, preventing them from traveling any significant distance. The universe was dark, not because there was no light, but because the light was trapped. This period lasted for about 380,000 years. Then, as the universe continued to expand and cool, it reached a critical temperature of about 3,000 Kelvin. At this point, the electrons had slowed down enough to be captured by the atomic nuclei, forming the first stable, neutral atoms. This event is known as recombination. Suddenly, the fog lifted. The universe became transparent to light. The photons that were present at that time were now free to travel unimpeded through space. And they have been traveling ever since. Their wavelengths stretched by the subsequent expansion of the universe from high-energy visible light into the cool, faint microwaves that we detect today. This is the cosmic microwave background, the oldest light in the universe. A beautiful, uniform glow that comes to us from all directions in the sky. It is a baby picture of our universe, a snapshot of the moment it first became transparent, a fossil that carries with it a wealth of information about the conditions of the early cosmos. The story of the Big Bang is a story of transformation, a story of how, from a state of almost perfect uniformity and simplicity, all the rich and complex structures we see today, the stars, the galaxies, the planets, and ourselves were gradually born. It is a story that is written in the light of the distant stars, in the composition of the elements, and in the faint, ancient glow of the cosmic microwave background. It is our story, as our journey through the cosmos brings us closer to the present day. We encounter the universe's most profound and perplexing mystery, the existence of dark energy. This is not a subtle, theoretical curiosity. It is the dominant component of our universe, making up roughly 68% of its total energy density. It is the invisible, silent force that is shaping the ultimate destiny of our cosmos, and we have almost no idea what it is. The discovery of dark energy in 1998 was a complete surprise. 2 independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using Type Ia supernovae as standard candles to measure the expansion rate of the universe at different times in its history. A Type Ia supernova is the thermonuclear explosion of a white dwarf star, and it always has the same intrinsic brightness, making it a perfect cosmic yardstick. The teams expected to find that the expansion of the universe was slowing down, as the mutual gravitational attraction of all the matter in the cosmos should be acting as a brake. To their astonishment, they found the exact opposite. The distant supernovae were dimmer than expected, which meant they were further away than they should have been if the expansion was slowing down. The expansion of the universe is accelerating. This groundbreaking discovery, which earned its leaders the 2011 Nobel Prize in Physics, implied the existence of a new, previously unknown form of energy with a strange and powerful property, a strong negative pressure that acts as a form of cosmic anti-gravity, pushing space-time apart. This is what we call dark energy. The simplest and most natural candidate for dark energy is the energy of the quantum vacuum itself, the zero-point energy we discussed earlier. In the context of Einstein's general relativity, a constant vacuum energy density would manifest as a cosmological constant, a term that Einstein himself had introduced into his equations in 1917, only to later retract it as his biggest blunder when Edwin Hubble discovered the universe was expanding. In a beautiful historical irony, modern cosmology has resurrected Einstein's blunder and made it the centerpiece of our standard cosmological model. A universe dominated by a cosmological constant has a strange and counterintuitive property. As space expands, the density of matter and radiation decreases as they are spread out over a larger volume, but the density of vacuum energy remains constant. This means that as the universe gets bigger, the total amount of dark energy increases. It is as if new energy is being created from the expanding space itself. In the early universe, when the density of matter and radiation was very high, the effects of dark energy were negligible. But as the universe expanded and thinned out, dark energy gradually became the dominant component. It took over from gravity as the primary driver of cosmic evolution about 5 billion years ago, and it has been accelerating the expansion ever since. The problem, as we have seen, is the vacuum catastrophe. The theoretical value of the vacuum energy calculated from quantum field theory is an absurd 120, orders of magnitude larger than the observed value of dark energy. This colossal discrepancy has led many physicists to believe that the simple identification of dark energy with vacuum energy must be wrong. This has led to a host of alternative theories. Perhaps dark energy is not a constant, but is a dynamic entity, a new quantum field dubbed quintessence that is slowly rolling towards its minimum energy state. In this scenario, the rate of cosmic acceleration could change over time, leading to a different ultimate fate for the universe. Or perhaps our understanding of gravity is wrong. Maybe general relativity needs to be modified on cosmological scales. These modified gravity theories attempt to explain the accelerated expansion without invoking any new form of energy. They propose that gravity itself becomes repulsive on very large distances. Distinguishing between these different possibilities is one of the primary goals of modern cosmology. Observatories like the Euclid Space Telescope and the Vera C. Rubin Observatory are designed to map the distribution of galaxies and the history of cosmic expansion with unprecedented precision, which will allow us to measure the properties of dark energy and to test whether it has changed over time. The nature of dark energy is not just a question for physicists. It is a question that touches on the ultimate fate of our universe. A universe dominated by a constant dark energy is destined for a big freeze. A universe dominated by a phantom energy that grows stronger over time is destined for a big rip. And a universe where dark energy could one day decay or change its sign could be destined for a big crunch. We live in a universe whose destiny is being written by an invisible, mysterious, and powerful force. A force whose true nature remains one of the greatest and most profound challenges in all of science. The empty space that surrounds us is not empty at all. It is a dynamic, energetic, and powerful entity, a cosmic protagonist whose story we are only just beginning to understand. The idea that our universe might not be the only one, that it could be part of a vast, perhaps infinite, multiverse, is a concept that has migrated from the realms of science fiction and philosophy into the heart of modern theoretical physics. It is a breathtaking and humbling idea, one that, if true, would represent the final and most profound step in the Copernican revolution. The long historical process of decentering humanity from a privileged position in the cosmos. The concept of the multiverse is not a single, coherent theory, but rather a consequence of several of our most ambitious and successful physical theories. We have already encountered one of its most compelling sources, the theory of eternal cosmic inflation. In this picture, our universe is just one bubble that formed when a small patch of an eternally inflating meta-universe decayed into a lower energy state. Other bubbles are constantly forming, each potentially with different physical laws, constants, and even different numbers of dimensions. This creates a vast, level 2 multiverse of disconnected, parallel realities. Another powerful argument for the multiverse comes from the many worlds interpretation of quantum mechanics. As we discussed, this interpretation, first proposed by Hugh Everett, solves the measurement problem by positing that the wave function never collapses. Instead, every quantum measurement causes the universe to split into multiple branches, with each branch corresponding to one of the possible outcomes. This creates a level 3 multiverse, a constantly branching tree of parallel realities. In this multiverse, there are an infinite number of yous, each living out the consequences of a different quantum outcome. There is a version of you who is reading this, and a version of you who decided to go for a walk instead. Every possibility is realized somewhere in this vast quantum multiverse. A third, and more straightforward and type of multiverse is the level Y multiverse. This is simply the idea that our observable universe, the region of space from which light has had time to reach us since the Big Bang, is just a small patch of a much larger, and possibly infinite, universe. If space is infinite, then in that infinite volume, every possible configuration of matter and energy must, by statistical necessity, repeat itself an infinite number of times. This means that somewhere out there, far beyond our cosmic horizon, there is another galaxy, another solar system, another Earth, and another you, an identical copy living out an identical life. And there are an infinite number of such copies. This is a staggering and deeply unsettling thought, one that challenges our sense of individuality and uniqueness. Finally, there is the most abstract and philosophical type of multiverse, the level 4 or mathematical universe proposed by physicist Max Tegmark. This is the idea that physical reality is, at its core, a mathematical structure, and since all consistent mathematical structures exist in a timeless, Platonic sense, then all possible mathematical structures exist as physical realities. Our universe is just one, particularly complex, mathematical structure, one that happens to have the right properties to allow for the emergence of self-aware substructures, like us, who can contemplate the mathematical nature of their own existence. The multiverse, in all its forms, provides a powerful, if controversial, framework for addressing the fine-tuning problem. The fact that the physical constants of our universe seem to be so exquisitely tuned to allow for the existence of life is no longer a miracle that requires a supernatural explanation. It is a simple selection effect. We find ourselves in a universe that is hospitable to life, because it is the only kind of universe we could find ourselves in. We are the survivors of a cosmic lottery of unimaginable proportions. The primary criticism of all multiverse theories is that they are, by their very nature, untestable. We can never travel to another bubble universe or communicate with a parallel branch of the quantum wave function. This has led some to argue that the multiverse is not a scientific theory, but a metaphysical one. But its proponents argue that the theories from which the multiverse arises, like inflation and quantum mechanics, are themselves highly testable. If these theories continue to pass every experimental test we throw at them, then we may be forced to take their more bizarre consequences, like the multiverse, seriously, and there may be indirect, circumstantial ways to search for evidence. The cosmic bruise from a collision with another bubble universe is one such possibility. The search for a variation in the fundamental constants of nature across the sky is another. Whether the multiverse is a physical reality or not. The very fact that it is a serious topic of discussion among many of the world's leading physicists is a testament to how far our cosmic horizons have expanded. It is a concept that forces us to confront the true scale of reality, to question our most basic assumptions about our own uniqueness, and to embrace a vision of the cosmos that is infinitely richer, stranger, and more magnificent than we ever dared to imagine. As we gaze out into the cosmos, our vision is fundamentally limited. The night sky appears as a vast, dark dome, but this is an illusion. We are not looking out at a static, three-dimensional space. We are looking back in time. The light from the moon takes a little over a second to reach us, so we see it as it was a second ago. The light from the sun takes 8 minutes. The light from our nearest stellar neighbor, Proxima Centauri, takes over 4 years. And the light from the Andromeda Galaxy, our closest major galactic neighbor, has been traveling for 2.5 million years. When we look at the most distant galaxies visible in the James Webb Space Telescope, we are seeing them as they were over 13 billion years ago, when the universe was just a toddler. This intimate connection between distance and time defines our cosmic horizon, because the universe has a finite age of approximately 13.8 billion years, and because light travels at a finite speed, there is a fundamental limit to how far we can see. The boundary of our observable universe is not a physical wall, but a temporal one. It is the distance from which light has had just enough time to reach us since the Big Bang. We can never, even in principle, see what lies beyond this horizon. The universe may be infinite, but our view of it is finite. The situation is made even more profound by the accelerating expansion of the universe. Not only is there a horizon that limits our view of the past, but there is also an event horizon that limits our view of the future, because space itself is expanding. And this expansion is accelerating. Distant galaxies are receding from us at ever-increasing speeds. There is a critical distance beyond which galaxies are receding from us, faster than the speed of light. This does not violate Einstein's theory of relativity, as it is space itself that is expanding, not the galaxies moving through space. But it does mean that any light emitted by those galaxies after they cross this event horizon will never be able to reach us. They will be causally disconnected from our future. They will, in a sense, disappear from our universe. The night sky of the far future will be a profoundly lonely place. As more and more galaxies recede beyond our event horizon, the cosmic landscape will become increasingly empty. Eventually, only the members of our own gravitationally bound local group of galaxies will remain visible. A future civilization, looking up at the sky, might conclude that they live in a single island universe, forever unaware of the vast cosmic ocean that we are privileged to still be able to see. This concept of an event horizon, a one-way membrane that separates the observable from the unobservable, is most famously associated with black holes. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape. Its event horizon is the point of no return. Any object or any information that crosses this boundary is lost to the outside universe forever. In the 1970s, Stephen Hawking revolutionized our understanding of black holes by showing that they are not completely black. Due to quantum effects at the event horizon, the constant creation and annihilation of virtual particle pairs from the quantum vacuum black holes should slowly emit a faint thermal radiation. This Hawking radiation causes the black hole to lose mass and, over immense timescales, to eventually evaporate completely. This brilliant theoretical discovery, which elegantly weaves together the principles of general relativity, quantum mechanics, and thermodynamics, also gave rise to one of the deepest paradoxes in modern physics, the black hole information paradox. According to the fundamental principles of quantum mechanics, information can never be destroyed. The total amount of information in a closed system must always be conserved. But if you throw an encyclopedia, with all its rich and complex information, into a black hole, that information seems to be lost forever behind the event horizon. And when the black hole evaporates, the Hawking radiation it emits appears to be purely thermal and random, containing no memory of the information that fell in. So, where does the information go? Is it truly destroyed, in violation of one of the most sacred principles of physics, or does it somehow escape, subtly encoded in the quantum correlations of the outgoing radiation? This paradox has been a major driver of research in theoretical physics for decades, and its resolution is thought to be a key step towards a full theory of quantum gravity. Recent theoretical work has suggested that the information is not lost, but is preserved on the event horizon itself, a concept related to the holographic principle, which posits that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary. The existence of horizons, both cosmological and black hole, is a profound and humbling feature of our universe. It tells us that there are fundamental built-in limits to our knowledge. There are parts of the cosmos and aspects of nature that may forever lie beyond the reach of our direct observation, but they are also a powerful spur to our theoretical imagination, forcing us to devise new and creative ways to understand the realities that are hidden from our view. They are a reminder that the universe is not a transparent, open book, but a deep and multi-layered mystery. A mystery whose most profound secrets are often hidden right at the very edge of what we can see. The grand narrative of our cosmos, as told by the standard Big Bang model, is a linear one. It is a story with a definite beginning, a long period of evolution, and a potential final end. But is this the only possible story? Could the universe be a more timeless, more cyclical entity, an eternal dance of creation and destruction, with no absolute beginning or end? This idea of a cyclic universe, of an endless dance of creation and destruction, is one of the oldest and most enduring ideas in human thought. It is found in the Kalpas of Hindu cosmology, vast time cycles of cosmic creation, maintenance, and dissolution. It is present in the philosophy of the ancient Stoics, with their idea of a great year, at the end of which the universe is consumed by fire and then reborn. And it is an idea that has been given a new scientific life in some of the most advanced and speculative theories of modern cosmology. The simplest version of a cyclic universe is one that ends in a big crunch. If the total density of matter and energy in the universe is high enough, then the mutual gravitational attraction will eventually overcome the cosmic expansion, causing the universe to slow down, stop, and then begin to contract, eventually collapsing back into a hot, dense singularity, a mirror image of the Big Bang. This singularity could then bounce, triggering a new Big Bang and a new cycle of expansion. This bouncing universe model was popular for a time, but it fell out of favor with the discovery of dark energy and the accelerating expansion of the universe, which seems to rule out an eventual collapse. It also suffers from a serious theoretical problem, the second law of thermodynamics. With each cycle, the entropy, or disorder, of the universe should increase. This means that each cycle should be longer and more diffuse than the last. And it is hard to see how a universe that has existed for an infinite number of cycles in the past could still be in the relatively ordered state we see today. But in the early 21st century, a new and more sophisticated version of the cyclic model was proposed by physicists Paul Steinhardt and Neil Turok. Their ekpyrotic, or cyclic model, is based on the ideas of string theory and extra dimensions. In this picture, our universe is a three-dimensional brane, or membrane, floating in a higher dimensional space, or bulk. There is another, parallel brane nearby. In this picture, the Big Bang is not the beginning of time, but is the result of a gentle periodic collision between our brane and this other brane. Each collision releases a tremendous amount of energy, which is converted into the hot, dense matter and radiation of a new cosmic cycle. After the collision, the branes move apart, and our universe expands and cools, just as in the standard Big Bang model. But the story does not end there. A form of dark energy. In this model, a potential energy between the branes eventually causes them to slow down and begin to move back towards each other, drawn together by a spring-like force. This leads, after a period of slow contraction, to another gentle collision, another Big Bang, and the beginning of a new cycle. Each of these cycles could last for 1 trillion years or more, an almost unimaginable timescale from a human perspective, but just a single beat in the eternal rhythm of the cosmos. This cyclic model has several elegant features. It avoids the initial singularity of the standard Big Bang model, as the branes themselves never reach infinite density. It can also explain the observed smoothness and flatness of our universe without the need for a period of cosmic inflation. The smoothness is a result of the long period of slow contraction before the last bang, which had plenty of time to smooth out any irregularities. It also provides a natural explanation for dark energy as the force that drives the cycles. The model also offers a potential solution to the entropy problem. The vast expansion that occurs during each cycle so dilutes the entropy that it becomes negligible, effectively resetting the cosmic clock. The cyclic model is still a minority view in the cosmological community, and it faces a number of significant theoretical challenges, particularly in describing the physics of the brane collision itself, a process that requires a full, and as yet unknown, theory of quantum gravity, but it remains one of the most compelling and well-developed alternatives to the standard inflationary Big Bang paradigm. It offers a vision of the cosmos that is not a one-off event, but an eternal, self-renewing, and resilient process. It is a vision that connects the frontiers of theoretical physics with some of the oldest and most profound intuitions of the human spirit. It is a reminder that the story of the universe may not have a beginning or an end, but may be a beautiful and endlessly repeating cosmic poem. The apparent, exquisite fine-tuning of the fundamental constants of nature to allow for the existence of life is one of the most puzzling and philosophically charged aspects of modern cosmology. It is as if we have walked into a cosmic casino and found that all the roulette wheels have been preset to the winning numbers: the strength of gravity, the mass of the electron, the value of the cosmological constant. If any of these numbers were even slightly different, the universe would be a sterile and lifeless place. This has led to the formulation of the anthropic principle, a controversial but powerful idea that attempts to explain this cosmic coincidence by appealing to our own existence as observers. The weak anthropic principle is a relatively straightforward and almost tautological statement. It simply says that the conditions we observe in the universe must be compatible with our own existence. We are here, we are conscious, we are made of carbon, and therefore, the universe must have properties that allow for the formation of carbon-based conscious observers. This is a form of selection bias. We are filtering the possible universes we could observe by the very fact of our own being. It is like a fish wondering why the world is so full of water. It is a valid, but not particularly deep, explanation. The strong anthropic principle, however, makes a much bolder and more metaphysical claim. It suggests that the universe is, in some sense, compelled to have properties that allow for the emergence of life and consciousness at some point in its history. This can be interpreted in several ways, from the theological, a divine designer, to the teleological, a cosmic purpose. The anthropic principle, in its weak form, finds a natural and scientific home in the context of the multiverse. If our universe is just one of a vast, perhaps infinite, ensemble of other universes, each with its own randomly assigned set of physical constants, then the fine-tuning problem dissolves. It is no longer a miracle that we find ourselves in a universe that is hospitable to life. It is a statistical inevitability. We are simply living in one of the rare, life-friendly bubbles in the vast, cosmic landscape of the multiverse. This is a powerful and elegant explanation, but it comes at a price. It requires us to accept the existence of a potentially infinite number of unobservable universes, a concept that many find to be a violation of the principle of Occam's razor, which states that we should not multiply entities beyond necessity. The debate between the multiverse anthropic explanation and the search for a more fundamental, unified theory that would uniquely determine the values of the constants is one of the central intellectual battles in modern theoretical physics. Is the universe the way it is because it is the only way it could be? Its properties fixed by a deep and elegant mathematical necessity? Or is it the way it is because it is just one of a vast ensemble of possibilities, and we are simply the lucky winners of a cosmic lottery? There are also alternative and more speculative approaches to the fine-tuning problem. The physicist Lee Smolin has proposed a model of cosmological natural selection. In this picture, universes can reproduce by creating new, baby universes inside the black holes that form within them. When a new universe is born, its fundamental constants can be slightly randomly mutated from those of its parent. Over many generations of universes, a process akin to biological natural selection would favor those universes whose constants are fitter, meaning they produce more black holes and therefore more offspring. Smolin argues that the same constants that lead to a high rate of black hole production, which requires a universe with long-lived stars, abundant carbon, and complex chemistry, are also the constants that are conducive to life. In this view, our life-friendly universe is not a random fluke, but the product of a long cosmic evolutionary history. The fine-tuning problem is a beautiful example of how a precise scientific observation can lead us to the deepest and most profound philosophical questions. It forces us to confront our own place in the cosmos, to ask whether our existence is a cosmic accident or a cosmic necessity, a random roll of the dice or the fulfillment of a deep, underlying purpose. And as you lie on the threshold of sleep, you can ponder the fact that your own conscious awareness is the very thing that makes this question possible, a single, precious point of view from which the universe can begin to contemplate its own mysterious and perhaps meaningful existence. The quest to understand the universe in its grandest sweep is a quest for unification. It is the search for a single, elegant, and comprehensive theory that can explain all the disparate phenomena of nature, from the dance of subatomic particles to the evolution of the cosmos, within a single, coherent mathematical framework. This was Einstein's dream, the goal he pursued for the last 30 years of an otherwise spectacularly successful scientific life, and it remains the holy grail of modern theoretical physics. The current state of our knowledge is a tale of two theories, general relativity and the standard model of particle physics. General relativity is Einstein's magnificent theory of gravity, a theory that describes gravity not as a force, but as the curvature of a dynamic, four-dimensional spacetime. It is a theory of the large scale, of planets, stars, galaxies, and the expanding universe. The standard model, on the other hand, is our theory of the small scale. It is a quantum field theory that describes the other three fundamental forces of nature: the electromagnetic force, the weak nuclear force, and the strong nuclear force, and all the known elementary particles, like quarks, leptons, and the Higgs boson. Both of these theories have been tested to an incredible degree of precision and have passed every experimental test with flying colors. They are, without a doubt, the two most successful scientific theories in the history of humanity. But they are fundamentally incompatible. They are written in different mathematical languages and are based on different physical principles. General relativity is a classical, deterministic theory of a smooth, continuous spacetime. The standard model is a quantum, probabilistic theory that plays out on a fixed, static spacetime background. This incompatibility becomes a critical problem in certain extreme regimes of nature, where both gravity and quantum effects are important. In the fiery crucible of the Big Bang, or in the infinitely dense singularity at the center of a black hole, our two great theories break down and give nonsensical, infinite answers. To understand these ultimate frontiers of reality, we need a new theory, a theory of quantum gravity that can seamlessly weave together the principles of general relativity and quantum mechanics. The search for this theory is the primary occupation of a large portion of the theoretical physics community today. One of the leading candidates, as we have seen, is string theory. In this ambitious framework, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. The different vibrational modes of these strings correspond to the different particles we see in nature. One particular vibration corresponds to the graviton, a hypothetical quantum particle of gravity. In this way, string theory naturally incorporates gravity into a quantum framework, but it does so at a price. The mathematical consistency of the theory requires the existence of extra, hidden dimensions of space, typically 6 or 7 of them, which are curled up into a tiny, complex Calabi-Yau manifold at every point in our familiar 3-dimensional space. The precise shape and size of these extra dimensions determine the properties of the strings, and therefore, the physical laws of our universe. String theory is a framework of breathtaking mathematical beauty and elegance, and it has the potential to unify all the forces and particles of nature. But it has, so far, failed to make any unique, testable predictions that would allow us to confirm or falsify it. The alternative approach is loop quantum gravity. Instead of starting with particles and trying to quantize gravity, loop quantum gravity starts with space-time itself and tries to quantize it directly. In this theory, space is not a continuous background, but is made of discrete quantum atoms of space, each with a volume of about the Planck length cubed. These atoms are connected together in a network called a spin network, and the evolution of this network in time creates a spin foam. Space-time, in this picture, is not a smooth fabric, but a dynamic, evolving quantum graph. Loop quantum gravity is a beautiful and conceptually radical theory, and it has had some notable successes, such as providing a calculation of the entropy of a black hole. But like string theory, it is still a work in progress, and it has struggled to show how the familiar, smooth spacetime of our macroscopic world can emerge from this underlying discrete quantum structure, and how the standard model of particle physics can be incorporated into its framework. The search for a unified theory of everything is one of the most difficult and ambitious endeavors in the history of science. It is a search that pushes the limits of our mathematics, our technology, and our very imagination. But it is a search that is driven by a deep and powerful faith, a faith that the universe, at its most fundamental level, is simple, elegant, and comprehensible. A faith that the two great, warring narratives of modern physics can, and must, one day be united into a single, beautiful, and complete story. The cosmological constant problem, the vacuum catastrophe, is more than just a numerical discrepancy. It is a deep, conceptual chasm that lies at the very heart of modern physics, a stark and humbling reminder of the vastness of our own ignorance. The problem, in its essence, is the collision of our two most successful physical theories, general relativity and quantum field theory, in the seemingly simple context of empty space. Quantum field theory tells us that the vacuum is not empty, but is filled with a seething sea of zero-point energy, the sum of the ground state energies of all the quantum fields that pervade the universe. When we try to calculate the energy density of this vacuum, using the principles of quantum mechanics, we get a number that is staggeringly large. General relativity, on the other hand, tells us that any form of energy is a source of gravity. It curves space-time. If the vacuum energy were truly as large as the quantum calculation suggests, its gravitational effect would be catastrophic. It would curve space-time so violently that the universe would have expanded into a diffuse, empty void in the first fraction of a second of its existence. There would be no stars, no galaxies, no planets, no us. But this is not what we observe. We observe a universe that is expanding and even accelerating, but at a rate that is incredibly, exquisitely slow compared to the theoretical prediction. The observed value of the cosmological constant, the energy density of the vacuum that is driving the cosmic acceleration, is about 120 orders of magnitude smaller than the naive theoretical calculation. This is a discrepancy of a 1 followed by 120 zeros. It is, without a doubt, the worst theoretical prediction in the entire history of physics. It is as if you tried to calculate the weight of a single grain of sand, and your answer was the weight of the entire Earth. Something is fundamentally and profoundly wrong with our understanding. The problem is not that we have two competing theories. It is that our two best theories, when combined, give a result that is spectacularly, absurdly wrong. There have been many proposed solutions to this profound puzzle, but none has gained widespread acceptance. The idea of supersymmetry, a hypothetical symmetry between the two fundamental classes of particles, bosons and fermions, offers a partial solution. In a perfectly supersymmetric world, the vacuum energy contributions from the bosons and the fermions would exactly cancel each other out, leading to a vacuum energy of zero. This is an elegant mathematical solution. The problem is that our world is not perfectly supersymmetric. If it were, we would have already discovered the superpartners of all the known particles, and we have not supersymmetry. If it exists, must be a broken symmetry, meaning the superpartners are much heavier than their standard model counterparts. A broken supersymmetry would no longer lead to a perfect cancellation, and while it could reduce the predicted value of the vacuum energy, it still requires an incredible amount of fine-tuning to get it down to the observed tiny value. Another, more philosophical approach is to appeal to the anthropic principle in the context of a multiverse. If there are an infinite number of bubble universes, each with a different, randomly determined value of the cosmological constant, then it is no surprise that we find ourselves in one of the rare universes where this value is small and positive, allowing for the formation of galaxies and life. In most other universes, the vacuum energy would be so large that they would either instantly collapse or expand into nothingness. This is a logically consistent explanation, but it is deeply unsatisfying to many physicists, as it abandons the hope of a fundamental physical explanation for one of the most important parameters of our universe. Other, more radical, proposals involve modifying the laws of gravity or quantum mechanics. Perhaps the vacuum energy does not gravitate in the same way as normal matter and energy. Perhaps our understanding of how to calculate the vacuum energy in quantum field theory is fundamentally flawed. The cosmological constant problem is a sign that we are missing a major piece of the puzzle. It is a crack in the foundations of modern physics, a crack through which the light of a new, deeper understanding may one day shine. Its resolution will likely require a full theory of quantum gravity, a theory that can consistently combine the principles of general relativity and quantum mechanics. And it is a problem that should instill in us a deep sense of intellectual humility. It is a reminder that even our most successful and well-tested theories are still just provisional approximations of a much deeper and far more mysterious reality. the empty space that surrounds us, the seemingly simple nothingness of the void, contains a secret that is so profound that it has, so far, defeated the collective intelligence of the most brilliant minds in the history of science. It is the ultimate puzzle, waiting patiently in the silence for a new Einstein to come along and solve it. The unidirectional flow of time, the arrow of time, is one of the most fundamental and yet most mysterious aspects of our experience. We are born, we live, we die, we remember the past, but not the future, because always precedes effect. This seems so obvious, so deeply ingrained in the fabric of our reality, that we rarely stop to question it. But when we look at the fundamental laws of physics, this arrow of time is nowhere to be found. The laws of Newtonian mechanics, of electromagnetism, of relativity, and even of quantum mechanics are all, with one minor exception related to the weak nuclear force, time symmetric. They work just as well for a movie played forwards as for a movie played backwards. If you were to film a collision between two billiard balls and play the movie in reverse, it would still look like a perfectly valid physical interaction. So Mike, if the fundamental laws of nature do not have a preferred direction of time, why does the macroscopic world of our experience so clearly do? The answer, as we have seen, lies in the second law of thermodynamics, the law of increasing entropy. The universe as a whole, and any isolated system within it, tends to evolve from a state of low entropy, high order, to a state of high entropy, high disorder. A whole egg is a low entropy state. A scrambled egg is a high entropy state. There are vastly more ways for the molecules of an egg to be arranged in a scrambled configuration than in an ordered, whole configuration. So the system, when left to its own devices, will naturally evolve towards the state of higher probability, the state of higher entropy. This gives time its thermodynamic arrow. But this just pushes the question back a step. Why was the universe in such an incredibly low entropy, highly ordered state to begin with? If the early universe, at the time of the Big Bang, had started in a state of thermal equilibrium, a state of maximum entropy, then nothing would have ever happened. There would be no arrow of time, no evolution, no complexity, no life. The fact that we live in a universe with a strong arrow of time is a direct consequence of the fact that it started in a state of extraordinary and seemingly improbable order. This is the ultimate cosmological puzzle, the past hypothesis. Why the low entropy beginning, the Austrian physicist Ludwig Boltzmann in the 19th century proposed a statistical explanation. Perhaps our observable universe is just a temporary, random fluctuation into a state of low entropy within a much larger and much older meta-universe, that is, for the most part, in a state of thermal equilibrium, a state of heat death. We just happen to live in a rare, ordered bubble. The problem with this idea, as was later pointed out, is that it leads to the bizarre Boltzmann's brain paradox. It would be statistically far more likely for a single, conscious brain with a full set of false memories of a past that never happened to fluctuate into existence for a brief moment, than for an entire, ordered universe like ours to do so. This makes the statistical fluctuation explanation seem deeply problematic. Modern cosmology has offered other, more sophisticated potential solutions. The theory of cosmic inflation, by stretching a tiny, smooth patch of the early universe to astronomical scales, can help to explain the homogeneity of our starting point, but it does not fully solve the problem of its low entropy. The British physicist Roger Penrose has proposed a bold and elegant solution in his theory of conformal cyclic cosmology. He argues that the far future of our universe, after an infinite amount of time has passed and all matter has decayed into a sea of massless photons, becomes geometrically indistinguishable from the hot, dense, low entropy state of a Big Bang for a new eon of the cosmos. In this picture, the universe goes through an infinite sequence of cycles, with the heat death of one eon becoming the low entropy Big Bang of the next. The arrow of time is reset with each new cycle. The quest to understand the origin of the arrow of time is a quest to understand the very origin of order, of structure, and of complexity in our universe. It is a question that connects the deepest principles of thermodynamics, cosmology, and quantum mechanics. And it is a question that is intimately tied to our own subjective experience of being. We are creatures of memory and anticipation, beings who are fundamentally oriented in time. Our consciousness is a process that is constantly weaving the raw data of the present into a coherent story that connects a remembered past with an imagined future. We are, in a very real sense, embodiments of the arrow of time. And as you lie on the threshold of sleep, as your own personal sense of time begins to dissolve into the timeless, dreamlike state of the unconscious, you can ponder this deep and beautiful mystery, the simple, familiar, and yet profoundly unexplained fact that time flows, that the universe evolves, that there is a difference between yesterday and tomorrow, may be the greatest and most wonderful miracle of all. The universe, in its grandest conception, may be far more complex and multi-layered than our familiar 3 dimensions of space and 1 of time would suggest. Some of our most ambitious and elegant physical theories, like string theory, require the existence of extra hidden dimensions to be mathematically consistent. This is a mind-bending idea, but it is one that has a long and respectable history in theoretical physics. The idea is that these extra dimensions are not like the large, extended dimensions we are familiar with. They are compactified, curled up into a tiny, complex geometrical shape at every single point in our space. Imagine a garden hose. From a great distance, it looks like a one-dimensional line. But as you get closer, you see that it has a second circular dimension that was previously hidden from view. In the same way, the extra dimensions of string theory are thought to be curled up on a scale so small, the Planck length, that they are completely inaccessible to our current experiments. The precise shape and size of these extra dimensions, the geometry of this Calabi-Yau manifold, is not just a mathematical curiosity, it is the key to everything. In string theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. The different ways these strings can vibrate correspond to the different fundamental particles we see in nature. An electron is a string vibrating in one pattern. A photon is a string vibrating in another. And the geometry of the extra dimensions determines which vibrations are possible, and what the properties of the resulting particles, their mass, their charge, their spin will be. The laws of physics are, in this sense, a consequence of geometry. This is a breathtakingly beautiful and ambitious idea. It has the potential to unify all the forces and particles of nature into a single, coherent framework, a theory of everything. The problem is that string theory does not predict a unique geometry for the extra dimensions. In fact, it allows for a vast and possibly infinite number of possible Calabi-Yau manifolds, a landscape of at least 10 to the power of 500 different possible vacuum states. each corresponding to a different set of physical laws. This has led to a deep split in the theoretical physics community. Some see this landscape problem as a fatal flaw in the theory, a sign that it is not a truly predictive theory, but a postdictive one that can be tweaked to fit any observation. Others, however, see it as the theory's greatest triumph. When combined with the idea of eternal inflation, the string theory landscape provides a physical basis for the multiverse. Each of the 10 to the power of 500 possible vacua could be realized in a different bubble universe, creating a vast ensemble of different physical realities. The anthropic principle then becomes a natural and powerful tool for explaining why we find ourselves in a universe with our specific set of physical laws. But the idea of extra dimensions has led to other, equally fascinating, cosmological models. The brain cosmology scenario, which we have touched upon, posits that our entire three-dimensional universe is a brain, a membrane floating in a higher dimensional bulk space. The forces and particles of the standard model are confined to our brain, like drawings on a sheet of paper, while gravity, the geometry of space-time itself, is free to propagate in the bulk. This could explain why gravity is so much weaker than the other forces. Its influence is being diluted by the extra dimensions. This scenario opens up a host of new and exciting possibilities. There could be other, parallel brains floating in the bulk, other universes separated from us by a tiny distance in a fourth spatial dimension. The Big Bang could have been the result of a collision between our brain and another. Dark matter could be the gravitational influence of matter on a nearby parallel brain. Dark energy could be the result of a force between the brains. These are speculative ideas, to be sure, and they are far from being experimentally verified. But they are not just idle fantasies. They are the logical consequences of taking our best physical theories seriously and following them to their ultimate conclusions. They are a testament to the power of the human imagination, guided by the rigor of mathematics, to conceive of realities that are far beyond the limits of our direct experience, and they serve as a profound reminder that the world we see, the familiar three dimensions of our everyday life, may just be a shadow, a projection, of a much richer, much deeper, and much more complex, multidimensional reality. As you close your eyes and your consciousness begins to detach from the familiar coordinates of your bedroom, you can let your mind drift into this higher dimensional space, a space where our entire universe is just a fragile membrane, a single note in a symphony played out in a reality whose true dimensionality we are only just beginning to imagine. The age-old dialogue between science and religion, between the empirical quest to understand the how of the universe and the spiritual quest to understand the why, has been one of the most fraught and also most fruitful in the history of human thought. The story of creation, the origin of the cosmos, has always been at the heart of this dialogue. For millennia, humanity has turned to its religious and mythological traditions to answer the ultimate questions of existence, the creation myths of the world. From the Genesis story of a six-day creation by an omnipotent God, to the Hindu concept of a cyclical universe born from the dream of Vishnu, are not scientific theories. They are profound, symbolic narratives that seek to provide a sense of meaning, of purpose, and of our place within a sacred cosmic order. Modern scientific cosmology, with its story of a 14-billion-year-old universe born from a Big Bang and governed by impersonal physical laws, can seem, at first glance, to be a direct and irreconcilable challenge to these ancient stories. This has led to a spectrum of responses. At one extreme, we find a position of conflict. Young Earth creationists who insist on a literal interpretation of the Genesis story reject the overwhelming scientific evidence for an old universe and for biological evolution. At the other extreme, we find a form of scientific materialism or scientism, which argues that science is the only valid path to knowledge and that religious beliefs are simply outdated, pre-scientific superstitions that should be abandoned. But between these two warring poles, there lies a vast and fertile ground for a more nuanced and constructive dialogue. Many scientists and theologians today advocate for a position of independence or non-overlapping magisteria. Noma, a term coined by the late paleontologist Stephen Jay Gould. In this view, science and religion are two distinct and legitimate domains of human inquiry that address different kinds of questions. Science deals with the empirical realm, with the how of the natural world. Religion deals with the realm of ultimate meaning, of morality, of purpose, the why of human existence. They are two different languages, two different ways of knowing, and they are not in inherent conflict because they are not trying to answer the same questions. A third position is one of dialogue or integration. In this view, science and religion are not just independent, but can actually enrich and inform each other. Theologians can learn from the discoveries of science, which can provide a more accurate and awe-inspiring picture of the created world. A picture that can deepen and refine their theological understanding. The discovery of a vast, ancient, and evolving universe, for example, can lead to a more mature and less anthropocentric understanding of the Creator. Scientists, in turn, can benefit from the deep, existential questions and the ethical frameworks that religion provides. Science can tell us how to clone a human being, but it cannot tell us whether we should. The great questions of meaning, of value, of purpose, which are often the initial motivation for a scientific career, are not in themselves. Scientific questions. The Catholic Church, for example, has had a long and complex relationship with science, but its modern position is one of dialogue and integration. The Big Bang theory was first proposed by a Catholic priest, Georges Lemaitre, and the Church today officially accepts the scientific accounts of the Big Bang and evolution as being compatible with Christian faith, seeing them as the means by which God's creative purpose unfolds in the world. In the Islamic tradition, there is a rich history of scientific inquiry during the Islamic Golden Age, and many contemporary Muslim thinkers are engaged in a vibrant dialogue between the Quranic worldview and the findings of modern science. And in the Eastern traditions, like Buddhism and Hinduism, the relationship is often even less fraught. The cyclical, vast, and non-theistic cosmologies of these traditions often have a more natural resonance with the worldview of modern physics than the linear creation ex nihilo stories of the Abrahamic faiths. The dialogue between science and religion is not about finding a single unified answer. It is about fostering a sense of intellectual humility, a recognition of the limits of our own ways of knowing, and an appreciation for the different and equally valuable paths that humanity has taken in its long and enduring quest to understand its place in the grand, mysterious, and sacred tapestry of the cosmos. The ultimate question, the one that lies beneath all of our scientific and philosophical inquiries, is the question posed by the philosopher Gottfried Wilhelm Leibniz in the 18th century. Why is there something rather than nothing? This is a question that seems to teeter on the very edge of reason. Nothing, in an absolute sense, is almost impossible for the human mind to conceive of. And yet, it seems, on the face of it, to be the simpler, more natural state, existence, with all its complexity, its laws, its beings, seems to demand an explanation. Why did the universe go to all the trouble of existing modern physics, as we have seen, has offered a scientific gloss on this question? The universe from nothing scenario in quantum cosmology suggests that our universe could have spontaneously tunneled into existence from a pre-existing quantum vacuum, a nothing that is not a true void, but a state of pure potential. This is a powerful and elegant idea, but it does not fully answer Leibniz's question. It simply pushes it back a step. It explains how our universe could have arisen from the quantum vacuum, but it does not explain why there is a quantum vacuum, with its specific laws and properties, rather than an absolute philosophical nothingness. To address this deeper question, some thinkers have turned to the realm of mathematics. The physicist Max Tegmark, in his mathematical universe hypothesis, has proposed a radical and breathtaking solution. The hypothesis states that physical reality is a mathematical structure, not just that it can be described by mathematics, but that its fundamental nature is mathematical. In this view, all possible, consistent mathematical structures have a real, physical existence. Our universe is just one such structure, a particularly complex and self-aware one. If this is true, then the question, why this universe, is answered. It exists because it is mathematically possible. The universe exists for the same reason that 2 + 2 = 4. For the same reason that the Pythagorean theorem is true. It exists by logical necessity. This is a form of ultimate Platonism. The idea that the abstract world of mathematical forms is the true, fundamental reality. This hypothesis also provides a natural home for the multiverse. All the different possible mathematical structures correspond to different universes, with different physical laws, particles, and dimensions. The fine-tuning problem is solved, and the existence of our universe is no longer a surprise, but a necessity. This is a deeply compelling idea, but it is also highly controversial and, at present, unfalsifiable. It blurs the line between physics and metaphysics in a way that many find uncomfortable. It raises deep questions about the relationship between the abstract and the concrete, between the map and the territory. Another, related approach, is the idea of an ultimate principle of sufficient reason. Perhaps the universe exists because it is, in some deep, logical sense, the simplest or most elegant possible reality. Or perhaps, as the philosopher Robert Nozick speculated, the state of nothingness is inherently unstable. Perhaps nothingness contains within it a force that nothings itself, leading inevitably to the existence of something. These are ideas that are on the very frontier of human thought, where the languages of physics, mathematics, and philosophy begin to merge. They are the modern, secular equivalent of the theological quest for God as the uncaused cause or the necessary being. Whether any of these approaches will ever lead to a final, satisfying answer is an open question. It is possible that the question, why is there something rather than nothing, is a question that is, in principle, unanswerable from within the system of existence. It may be a question that is designed not to be solved, but to be held, to be contemplated, to be a source of endless wonder and humility. And as you lie in the quiet of the night, the verge of sleep, you can feel the weight and the beauty of this ultimate mystery. The very fact that you exist, that you are a conscious, questioning being in a universe of something, is a miracle that is either the result of a random, inexplicable chance or the expression of a deep, beautiful, and inescapable logical necessity. The choice between these two perspectives may be the most fundamental choice of all. Our long and winding journey through the origin of the universe, from the quantum foam to the multiverse, from the Big Bang to the arrow of time, has been a journey through the landscape of modern science. But this entire landscape, with all its theories, its data, its equations, is ultimately perceived, conceived, and understood through the lens of one of the most mysterious and profound phenomena in the entire cosmos, our own, human consciousness. We have spoken of the observer in quantum mechanics. But what is this observer? Is it a simple mechanical measuring device? Or is there something special, something fundamental, about the role of a conscious mind in the unfolding of reality? This is a question that has haunted the fringes of physics for a century, and it is one that is now beginning to move closer to the center of scientific inquiry. The hard problem of consciousness, the question of how a physical system like the brain can give rise to the rich, subjective, and qualitative world of our inner experience, remains one of the greatest unsolved challenges in all of science. The classical materialistic view, which sees the brain as a complex biological computer and consciousness as an emergent property of its information processing, has, so far, failed to provide a convincing explanation for the raw feel of experience. This has led some thinkers to propose that consciousness may not be an emergent property of complexity, but a fundamental property of the universe, on par with space, time, and mass. This is the essence of panpsychism, the ancient idea that mind, in some rudimentary form, is a ubiquitous feature of reality. In this view, an electron does not just have a physical aspect, but also a mental aspect, a tiny, primitive flicker of proto-consciousness. As matter becomes more complex and organized, as in a living cell or a human brain, these tiny flickers of mind can combine and integrate, giving rise to the rich, self-aware consciousness that we experience. This is a radical idea, but it is one that is gaining a new respectability as a potential solution to the hard problem. It avoids the seemingly impossible task of trying to get consciousness to emerge from purely non-conscious ingredients. Instead, it suggests that consciousness has been there all along, woven into the very fabric of the cosmos. The theory of orchestrated objective reduction, OR, proposed by Roger Penrose and Stuart Hameroff, offers a specific physical mechanism for how this might work. It suggests that consciousness is a quantum computational process occurring in the microtubules of our brain's neurons, a process that is intimately linked to the fundamental Planck-scale geometry of spacetime. In this model, each moment of conscious awareness is a quantum collapse event, a moment where the superpositional potential of the brain's quantum state is resolved into a definite, classical experience. This is a bold and speculative theory, but it is one that makes testable predictions, and it is a beautiful example of how the mysteries of the quantum world and the mysteries of the mind might be two sides of the same deep coin. Another related idea is that of the universe as a vast information processing system. The physicist John Wheeler's famous dictum, it from bit, suggests that the fundamental reality is not matter or energy, but information, and that the physical world is a manifestation of this underlying informational reality. In this view, consciousness is not just a processor of information. It is, in some sense, the very medium through which information acquires meaning and becomes reality. This is the essence of Wheeler's participatory anthropic principle, the idea that the universe, through the emergence of conscious observers, brings itself into being. We are not just spectators of the cosmic drama. We are participants, co-creators of the story. The questions we ask, the observations we make, the meaning we find, these are not just reflections of a pre-existing reality. They are an integral part of its ongoing creation. As you lie on the threshold of sleep, as your own individual consciousness begins to dissolve and merge into the vast, mysterious realm of the unconscious, you can ponder this profound and beautiful possibility. The very consciousness that is listening to these words, that is contemplating the origin of the universe, may not be just a fleeting, accidental byproduct of a random chemical process on a small, insignificant planet. It may be a fundamental, necessary, and creative aspect of the cosmos itself, a tiny, precious window through which the universe comes to know, to feel, and to wonder at its own magnificent existence. Our exploration of the cosmos, both in its vast outer reaches and its deep inner nature, inevitably brings us to the edge of our own knowledge, to the horizon of what we can see and what we can know. We have peered back in time to the faint, ancient light of the first galaxies. We have conceived of realities beyond our own observable universe, of multiverses and extra dimensions. We have even dared to ask what might have come before the beginning of time itself. But in this quest, we are always confronted with our own fundamental limitations. The cosmic particle horizon, the boundary of our observable universe, is a real and seemingly insurmountable barrier. We can never directly see the regions of space that lie beyond it. The cosmic event horizon, created by the accelerating expansion of the universe, is an even more final boundary, a one-way membrane that will forever hide the most distant parts of the cosmos from our view. The Planck scale, the realm of quantum gravity, represents a fundamental limit to the resolution with which we can probe the fabric of space-time, and the very nature of scientific inquiry, with its reliance on testable, falsifiable hypotheses, may mean that some of the grandest and most compelling ideas of modern cosmology, like the multiverse, will forever remain in the realm of metaphysics. But these limitations are not a cause for despair. On the contrary, they are a source of profound intellectual humility and a powerful spur to our creativity. The history of science is a history of pushing boundaries, of finding clever, indirect ways to probe the realities that lie beyond our direct grasp. We cannot see a black hole, but we can infer its presence from the dance of the stars that orbit it, and from the gravitational waves it emits when it collides with another. We cannot see an exoplanet's surface, but we can deduce the composition of its atmosphere from the faint starlight that filters through it. In the same way, physicists are constantly devising new and ingenious ways to search for the indirect, circumstantial evidence of the realities that lie beyond our current horizons. They are searching for the cosmic bruises in the CMB that could signal a collision with another universe. They are looking for the subtle signatures of extra dimensions in the behavior of particles at the Large Hadron Collider. They are listening for the faint, primordial whisper of gravitational waves from the moment of inflation. This is a quest that requires patience, ingenuity, and a deep appreciation for the subtle art of scientific inference. It is a quest that acknowledges its own limits, but refuses to be bound by them. And this quest is not just about expanding our knowledge of the external world. It is also about expanding our understanding of ourselves. The realization that we live in a universe with fundamental horizons, that our knowledge will always be partial and incomplete, can be a powerful antidote to the arrogance and dogmatism that have so often plagued human history. It invites us to adopt a stance of openness, of curiosity, of wonder. It reminds us that the universe is not a problem to be solved, but a mystery to be lived. And as we stand on the shore of this vast, cosmic ocean of the unknown, we are not alone. We are part of a long, unbroken chain of human inquiry. A chain that stretches back to our most ancient ancestors who first looked up at the night sky and wondered. We are the inheritors of their questions and the custodians of their legacy. And as you surrender to the gentle, restorative mystery of sleep, you can feel the sense of connection to this great human adventure, the very consciousness that is about to drift into the timeless, boundaryless realm of dreams is the same consciousness that has dared to ask the biggest questions, to imagine the grandest possibilities, and to reach for the stars. The journey is far from over. The greatest discoveries, the most profound revelations, may still lie ahead, waiting patiently for us in the deep, silent, and beautiful darkness that lies just beyond the horizon of our current understanding. The golden age of cosmology in which we are now living is a testament to the power of human ingenuity and our insatiable desire to understand our place in the cosmos. With a new generation of powerful telescopes, gravitational wave detectors, and particle accelerators, we are poised to answer some of the longest-standing questions in science, and, in the process, to uncover new mysteries that we cannot yet even imagine. The James Webb Space Telescope, with its unparalleled sensitivity in the infrared, is already revolutionizing our view of the early universe. In the coming years, it will continue to push our observational frontier ever closer to the Big Bang, searching for the light of the very first stars and galaxies, the cosmic dawn when the universe first lit up. It will provide us with detailed chemical fingerprints of the atmospheres of hundreds of exoplanets, searching for the telltale signs of life beyond Earth. It will peer into the dusty hearts of stellar nurseries and protoplanetary disks, giving us an unprecedented view of the birth of stars and worlds. On the ground, a new generation of massive 30-meter class optical telescopes, like the giant Magellan telescope and the 30-meter telescope, will provide a synergy with Webb, allowing for high-resolution follow-up observations of the most interesting objects it discovers. In the realm of radio astronomy, the Square Kilometre Array, a continent-spanning network of thousands of radio antennas, will map the distribution of neutral hydrogen in the early universe, providing a three-dimensional picture of the cosmic web and the epoch of ionization, the period when the light from the first stars and quasars ionized the neutral gas that filled the cosmos. The search for the nature of dark matter and dark energy will enter a new phase of precision, the Vera C. Rubin Observatory, with its vast 8.4-meter mirror and its 3.2 gigapixel camera, will survey the entire southern sky every few nights for a decade, creating the deepest and widest map of the universe ever made. Its data will allow us to trace the history of cosmic expansion with unprecedented accuracy, to map the distribution of dark matter through weak gravitational lensing on a vast scale, and to search for the fleeting signatures of transient events like supernovae and kilonovae. The Euclid Space Telescope will provide a complementary, high-resolution view, mapping the shapes of billions of galaxies to study the subtle distortions caused by dark matter and dark energy. The detection of gravitational waves has opened a completely new window onto the universe, a window that allows us to hear the cosmos, not just see it. The current network of LIGO, Virgo, and Cagra detectors will be upgraded to increase their sensitivity, allowing them to detect the faint ripples in space-time from more distant and more exotic cosmic cataclysms. And in the 2030s, the Laser Interferometer Space Antenna LISA, a constellation of 3 spacecraft flying in a triangular formation millions of kilometers apart, will take gravitational wave astronomy into space. LISA will be sensitive to the low-frequency gravitational waves emitted by the mergers of supermassive black holes in the centers of distant galaxies, and potentially to the faint, stochastic background of gravitational waves from the very first moments of the Big Bang itself. This could provide a direct, unambiguous confirmation of cosmic inflation and a glimpse into the physics of the universe at energies far beyond the reach of any terrestrial particle accelerator. On the theoretical front, the quest for a theory of quantum gravity will continue, guided by the subtle clues provided by these new observations, and perhaps by the new computational power of quantum computers, which could one day allow us to simulate the complex dynamics of quantum spacetime directly. This is a moment of unprecedented opportunity in the history of science. We are living at a time when we have the tools, the theories, and the global collaborative spirit to address some of the deepest and most profound questions that humanity has ever asked. The journey is long, the challenges are immense, and the ultimate answers may forever lie just beyond our grasp. But the quest itself, the shared human endeavor to understand our cosmic home, is one of the noblest and most beautiful expressions of our species. It is a quest that connects us to our past, gives meaning to our present, and inspires our hopes for the future. And as you close your eyes and let the universe of your own mind unfold in the quiet theater of your dreams, you can feel a sense of participation in this grand human adventure. The consciousness that is about to journey into the mysterious, inner cosmos of sleep is the same consciousness that is, at this very moment, reaching out to the stars, listening for the echoes of creation, and striving to read the silent, beautiful, and endlessly fascinating story of the universe. Good night, and may your dreams be as vast and as wonderful as the cosmos itself.
A photon, a single particle of light, leaves a nascent star in a galaxy that has only just begun to assemble itself from the primordial dust of a young cosmos. This particle travels for 13 billion years across an expanding void, its path bent by the gravity of invisible matter, its energy stretched by the very fabric of space, until it completes its journey in a quiet corner of our solar system, captured by a golden mirror 1 million miles from Earth. This is not a poetic abstraction. It is the physical reality of what the James Webb Space Telescope does every second of every day. It is a time machine, and the images it sends back are not just pictures, but relics, ghosts of a past so ancient that the light from these objects has journeyed longer than our planet has existed. We built this telescope to answer the foundational questions of our existence. Where did we come from, and are we alone? But the answers it has begun to deliver are far stranger and more profound than we ever anticipated. The very first deep field images were not a gentle confirmation of our existing models. They were a shock to the system, a rupture in our understanding of cosmic history. Our theories, built on decades of observation and calculation, predicted that the earliest galaxies should be cosmic infants, small, chaotic, misshapen clusters of gas and stars struggling to coalesce in the turbulent aftermath of the Big Bang. We expected to see cosmic toddlers, fumbling their way toward maturity. Instead, Webb showed us young adults. It unveiled galaxies from just a few 100 million years after the beginning of time that were already shockingly structured, with well-defined spiral arms, organized central bulges, and furious rates of star formation. This was not a minor discrepancy. It was a fundamental challenge to our timeline of cosmic evolution. It was as if we had discovered evidence of Roman aqueducts in a prehistoric cave. The existence of such complexity so early in the universe's life suggests that the processes of galaxy formation are either far more rapid or began far earlier than our models allowed. The delicate dance of gravity, gas dynamics, and dark matter that we thought took billions of years to choreograph seems to have occurred in a cosmic heartbeat. This single observation has sent shockwaves through the astronomical community, forcing a re-examination of everything from the initial conditions of the universe to the very nature of the matter that governs its structure. It raises a tantalizing and deeply unsettling possibility. Perhaps the universe itself is significantly older than our current estimate of 13.8 billion years. This age is not an arbitrary number. It is a cornerstone of modern cosmology. Derived from precise measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, and the rate at which the universe is expanding, a value known as the Hubble constant. But if galaxies had time to become so mature so early, it implies that the clock may have been ticking for longer than we thought. This isn't just about adding a few billion years to the cosmic calendar. A different age for the universe would mean that the rate of expansion has been different. The density of matter and energy has evolved differently, and the entire story of our cosmic origins would need to be rewritten. We are now in a state of profound and exciting uncertainty, where the very foundations of our cosmological model are being questioned, not by a lack of data, but by the astonishing clarity of the data Webb is providing. The telescope was designed to show us the how of the universe, but it has started by forcing us to reconsider the when. This initial surprise is not an endpoint, but a beginning, a harbinger of the paradigm shifts to come as Webb continues to peer deeper into the dawn of time, revealing a universe that is not just older, but stranger and more creatively potent than we ever dared to imagine. The history of science is a history of overturned assumptions, and Webb is proving to be our most powerful tool for this necessary act of intellectual demolition and reconstruction. We are not just observing the universe, we are being forced to rethink it from its very first moments. The light from those first stars carries a message, and that message appears to be that our story is longer, and our cosmic origins more mysterious than we ever knew. The cosmic timeline is not the only grand narrative being challenged by these new dispatches from the early universe. Our own sense of place, our galactic identity, has been fundamentally altered. For decades, the Milky Way was held up as a venerable elder, one of the first great spiral galaxies to form, a cosmic benchmark against which other, younger galaxies were measured. Webb has shattered this comforting illusion. It has discovered galaxies that are not only older than our own, but were already vast and structurally complex when the universe was but a fraction of its current age. Finding a galaxy older than the Milky Way is akin to an archaeologist discovering a fully formed medieval castle buried beneath the foundations of a simple Stone Age hut. It defies the expected sequence of development and forces a radical reevaluation of how such structures could possibly form. The standard model of galaxy formation is a hierarchical one, known as the bottom-up model. In this picture, small, dwarf-like protogalaxies form first from collapsing clouds of gas and dark matter. Over billions of years, these smaller structures merge and collide, their gravitational interactions slowly building them up into the grand spiral and elliptical galaxies we see today. It is a slow, patient, and cumulative process. But the existence of these ancient, massive galaxies, which some astronomers have nicknamed universe breakers, directly contradicts this picture. They suggest a top-down formation process might also be at play, where vast clouds of gas could collapse directly and rapidly into massive galactic disks, bypassing the slow, incremental merger phase entirely. This would require a set of physical conditions in the early universe: higher gas densities, different temperature gradients, perhaps a different behavior of dark matter that our current models do not fully account for. The implications are staggering. If massive galaxies can form this quickly, it means that the conditions for star formation, planet formation, and even the chemical enrichment necessary for life could have been in place much earlier in cosmic history than we thought possible. We are not just observing galaxies, we are watching the universe's creative potential unfold at a speed that borders on the miraculous. The challenge now for astrophysicists is to build new simulations, new theoretical frameworks that can accommodate this accelerated timeline. It may be that the interplay between the first supermassive black holes and their host galaxies played a much more significant role, acting as gravitational anchors and engines of star formation that jump-started the process. Or perhaps the very nature of dark matter, the invisible 85% of the universe's mass, is different from what we assume. Maybe it interacts with itself or with normal matter in ways that promote faster collapse and structure formation. Whatever the answer, the discovery of these cosmic elders has demoted our own Milky Way from a primordial founder to just one of many, perhaps even a relative latecomer to the galactic stage. It is a lesson in cosmic humility, a reminder that the universe is not required to conform to our expectations or our timelines. The light from these ancient galaxies tells a story of a universe that was in a hurry, a cosmos that was building grand structures and complex systems, while our own corner of space was still a formless cloud of gas and dust. We are the descendants of a universe that was far more dynamic and efficient in its youth than we ever gave it credit for. The redrawing of the cosmic map extends beyond the chronology of galaxies and into the very architecture of space-time itself, in what was once considered the great empty voids of the universe. Webb has uncovered a structure so colossal, so utterly gargantuan, that it challenges the most fundamental assumption of modern cosmology, the cosmological principle. This principle posits that, on the largest scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and from all locations. It is the bedrock upon which the entire standard model of cosmology is built. But Webb has found a wall, not a literal wall, but a vast interconnected filament of galaxies, gas, and dark matter stretching for billions of light years, a cosmic superhighway that dwarfs any previously known structure. This cosmic wall is not just a statistical anomaly, it is a feature so large that it should not have had time to form in the 13.8 billion years since the Big Bang, even with our most generous models of gravitational collapse. Its existence suggests that the universe may not be as uniform as we believed. It may have a grain, a texture, a large-scale architecture that hints at organizing principles we have yet to discover. The formation of such a structure might be tied to the initial quantum fluctuations that seeded the universe during the period of cosmic inflation. Perhaps some of these initial ripples were not random, but were correlated over vast distances, creating a preferred axis or plane along which matter would later coalesce. This would be a profound discovery, as it would mean that the randomness of the quantum vacuum from which our universe emerged was not entirely random after all, but contained a blueprint for the cosmic web we see today. Alternatively, the cosmic wall could be evidence of a more exotic physics. Some theories propose the existence of cosmic strings, one-dimensional topological defects left over from the phase transitions of the early universe. These strings, incredibly dense and stretching across the cosmos, could act as gravitational seeds, their immense gravity pulling in matter to form these vast, linear structures. While purely theoretical, the discovery of a structure like the cosmic wall lends a new urgency to the search for such phenomena. NASA and other international agencies are now dedicating observational resources to map the extent and composition of this wall, to understand if it is a singular feature or part of an even larger, unseen pattern. If the universe is indeed structured in this way, with vast walls and interconnected filaments separated by immense voids, then our understanding of gravity, dark matter, and dark energy may need to be fundamentally revised. Gravity, as described by Einstein, works the same everywhere, but what if, on these unimaginable scales, its behavior changes, or what if the properties of dark matter are not uniform, but vary depending on the density of the environment? The cosmic wall is more than just a large collection of galaxies. It is a direct challenge to our most cherished principles, a silent, monumental testament to the possibility that the universe is governed by rules that are far more complex, and perhaps far more elegant, than our current theories can accommodate. It forces us to confront the possibility that our view of a smooth, uniform cosmos is an illusion born of our limited perspective, and that the true reality is a far grander, more structured, and more mysterious tapestry than we ever imagined. In the midst of this cosmic remapping, amidst the discovery of ancient galaxies and impossibly large structures, Webb has also detected a whisper, a signal from the deep dark that is as enigmatic as it is tantalizing, from a distant, unidentified source. The telescope has recorded a series of mysterious light signals, pulses that are unlike any known astronomical phenomenon. These signals are not the chaotic bursts of a supernova or the regular lighthouse-like spin of a pulsar. They exhibit a complex, repeating pattern, a structured sequence that seems to defy a natural explanation. The scientific community is, rightly, exercising extreme caution. The history of astronomy is littered with signals that were initially thought to be of intelligent origin, only to be later explained by a newly discovered natural phenomenon. The first pulsars were playfully nicknamed LGM-1 for little green men before their nature as rapidly spinning neutron stars was understood. And so, the leading hypotheses for these new signals remain grounded in known, if extreme, physics. Could they be originating from a new type of celestial object, perhaps a magnetar with a complex magnetic field that modulates its emissions in a periodic way? Or could they be the result of a binary system of two compact objects, like neutron stars or black holes, whose orbital dance creates a complex pattern of gravitational lensing, causing the light from a background source to flicker in a structured way? These are all plausible, if unproven, explanations. NASA has put observatories around the world on alert, hoping to capture the signal across different wavelengths of the electromagnetic spectrum, from radio waves to gamma rays, to triangulate its position and analyze its properties in more detail. This multi-messenger approach is crucial to solving the mystery. A natural source would likely have a broad spectrum of emissions, while an artificial signal might be narrowly focused on a specific frequency, a telltale sign of an efficient, engineered beacon. But while the scientific process moves forward with its necessary rigor, the philosophical implications of the signal are impossible to ignore. The very possibility, however remote, that these signals are a product of intelligence is a thought that changes everything. It would be the single greatest discovery in human history, a definitive end to our cosmic solitude. It would force a reevaluation of our place in the universe, our purpose, and our future. For this reason, the search for an explanation is being pursued with an intensity and a global collaboration rarely seen in science. The signal is a puzzle, wrapped in a mystery, inside an enigma, but it is a puzzle that humanity is now united in trying to solve. Whether its origin is a new wonder of astrophysics or the first greeting from a distant intelligence, the outcome will be revolutionary. If it is natural, it will reveal a new process in the universe, a new way in which matter and energy can interact. If it is artificial, it will reveal that we are not alone. Either way, the universe has spoken, and we are listening. The silence of space has been broken by a whisper, and that whisper may carry the answer to the oldest and most profound question we have ever dared to ask. The mystery of the signal is a powerful reminder that our search is not just for planets and stars, but for meaning, for connection, for a sign that in this vast, dark expanse, there is another mind looking back at us, wondering, just as we are, about the nature of it all. While the grand cosmic narratives of time, space, and life are being rewritten on the largest scales, Webb has also turned its golden eye to our own galactic neighborhood, and what it has found there is no less revolutionary. In a star system surprisingly close to our own, it has discovered a world that feels hauntingly familiar, a planet, nestled squarely in its star's habitable zone, that is not just a rocky sphere, but a world with an atmosphere, a world with weather, a world that may hold liquid water. The initial analyses of this planet's atmosphere have been nothing short of breathtaking. Using a technique called transit spectroscopy, where the telescope measures the starlight filtering through the planet's atmosphere as it passes in front of its star, Webb has detected the unmistakable chemical fingerprints of carbon, oxygen, and, most excitingly, water vapor. These are the fundamental ingredients for life as we know it. But it is the combination and the ratios of these gases that have truly captured the scientific community's imagination. The presence of both oxygen and methane in the same atmosphere is particularly significant. These two gases are chemically reactive and, on geological timescales, should destroy each other. On Earth, the only reason we have a stable, oxygen-rich atmosphere with traces of methane is because life is constantly replenishing them. Photosynthesis pumps out oxygen, while biological decay and digestion produce methane. Finding this specific chemical disequilibrium on another world is one of the strongest potential biosignatures we could hope for. It is not yet definitive proof of life. There could be unknown geological or photochemical processes that mimic biology, but it is a flashing green light, an invitation to look closer. NASA is now dedicating a significant portion of Webb's observational time to this single world, hoping to build a detailed map of its atmospheric composition, to search for seasonal variations that could indicate a global biosphere, and to even try and detect the glint of sunlight off a potential ocean, a phenomenon known as glints. The discovery of this world has moved the search for extraterrestrial life from the realm of abstract probability to a tangible, scientific quest with a specific target. It has also brought the dream of human expansion into sharper focus. While interstellar travel remains the stuff of science fiction, the existence of a potentially habitable world so close by provides a powerful, aspirational goal for future generations. It raises profound questions about our long-term survival and our responsibilities as a species. If we find life there, do we have the right to interfere? If we find it to be sterile, do we have the right to colonize it, to turn it into a second Earth? These are no longer just philosophical thought experiments, they are becoming practical, ethical dilemmas that we may have to face in the coming centuries. The discovery of this pale blue dot in a nearby star system is a mirror held up to our own world. It reminds us of the preciousness and fragility of our own biosphere, and it challenges us to become a species worthy of a cosmic destiny. The light from this nearby world tells us that planets like ours may not be a cosmic rarity, and that the conditions for life may be more common than we ever thought. It is a message of hope, a whisper from a neighboring shore that suggests we may not be the only ones to look up at the stars and wonder. And in a universe that often feels vast, cold, and indifferent, that message of hope may be the most important discovery of all. The search for life beyond Earth is also a search for ourselves, for our place in the grand tapestry. And this nearby world has just given us the most promising thread we have ever found. The fabric of our cosmic understanding, woven from threads of theory and observation, is being stretched to its breaking point not just by the unexpected maturity of the early universe, but by the very dynamics of its expansion. For decades, the Hubble constant, the measure of how fast the universe is expanding, has been a cornerstone of cosmology. It is the key that unlocks the universe's age, its size, and its ultimate fate. But it is a key that no longer seems to fit the lock. There is a crisis in cosmology, a growing and persistent tension between two different, highly precise methods of measuring this fundamental constant. The first method looks at the late universe. It uses objects with known intrinsic brightness, like Cepheid variable stars and Type Ia supernovae, as standard candles. By measuring how dim these candles appear from Earth, we can calculate their distance, and by measuring their redshift, the stretching of their light as they move away from us, we can calculate their speed. This method, refined over decades, and now honed to an incredible precision by telescopes like Hubble and Webb, gives us a value for the expansion rate of the local universe. The second method looks at the early universe. It studies the cosmic microwave background, the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. The tiny temperature fluctuations in the CMB contain a wealth of information about the universe's initial conditions, its density, its composition, and its initial rate of expansion. By plugging these initial conditions into our standard cosmological model, called lambda CDM, we can predict what the expansion rate should be today. And here is the crisis: the two numbers do not match. The late universe measurement suggests the universe is expanding about 9% faster than the early universe prediction. This is not a small rounding error, it is a 5 sigma discrepancy, a statistical level that in particle physics would be hailed as a definitive discovery. Something is fundamentally wrong. Either our measurements are flawed in some subtle, systematic way we do not understand, or our standard model of cosmology, the theory that has guided our understanding for a generation, is incomplete. Webb's role in this crisis is pivotal. Its incredible resolution allows it to measure the standard candles in the late universe with unprecedented accuracy, eliminating many of the potential sources of error that have plagued previous measurements. And its initial findings have not resolved the tension, they have sharpened it. The faster expansion rate appears to be real. This forces us to confront the possibility that our lambda CDM model is missing a key ingredient. The model is built on just a few key components: normal matter, and dark energy. But what if there is something else? Perhaps there was a period of early dark energy, a new form of energy that was present in the first few 100,000 years of the universe's life, which gave the cosmos an extra kick of expansion before it dissipated. This would change the initial conditions inferred from the CMB, potentially bringing the early and late universe measurements into alignment. Or perhaps dark matter is not as simple as we think. Maybe it is not a single inert particle, but a whole family of particles with complex interactions that have changed over cosmic time. A different behavior of dark matter in the early universe could alter the way sound waves propagated through the primordial plasma, which would in turn change our interpretation of the CMB data. Even more radically, some physicists have proposed that Einstein's theory of general relativity itself may need to be modified on cosmological scales. While it works perfectly in the solar system and for phenomena like gravitational lensing, it is possible that on the scale of the entire universe, gravity behaves differently, leading to a different expansion history. This is a path most scientists are reluctant to take, as general relativity is one of the most successful and well-tested theories in the history of science, but the persistent Hubble tension is forcing us to consider even the most outlandish possibilities. The resolution of this crisis, whatever it may be, will mark a new era in cosmology. It will either reveal a new component of the universe, a new law of physics, or a new understanding of our cosmic history. Webb is at the heart of this investigation, providing the crucial, high-precision data that will either break the standard model or reveal the subtle flaw in our measurements that has led us astray. The faster expansion rate is not just a number, it is a clue, a breadcrumb leading us into a deeper, richer, and more complex understanding of the universe. It tells us that the cosmic story is still unfolding, and that there are new chapters, perhaps even new characters, that we have yet to discover. The universe is not just expanding, it is expanding in a way that challenges our deepest theories, forcing us to be more creative, more rigorous, and more open-minded in our quest to understand its ultimate nature. The implications of this accelerated expansion ripple outwards, touching not just the beginning of the universe, but its ultimate end. The fate of the cosmos is intimately tied to the nature of dark energy, the mysterious force that appears to be driving this expansion. In our standard model, dark energy is represented by the cosmological constant, an intrinsic energy of space-time itself. In this scenario, the density of dark energy remains constant as the universe expands. As matter and radiation become more dilute, dark energy becomes the dominant component of the universe's energy budget, leading to an endless, accelerating expansion. The ultimate fate in this model is a heat death or big freeze. Galaxies will recede from each other until they are so far apart that their light can no longer reach us. The sky will become dark, empty, and cold. The last stars will burn out, their fuel exhausted. Black holes will slowly evaporate over trillions of years through Hawking radiation. The universe will settle into a final state of maximum entropy, a cold, uniform, and eternal darkness, where nothing ever happens again. It is a bleak, but scientifically plausible end. However, the data from Webb, suggesting a faster than expected expansion, opens the door to other, more dramatic possibilities. What if dark energy is not a constant? What if its density is increasing over time? This hypothetical form of energy is known as phantom energy, and it leads to a far more violent end, the Big Rip. In this scenario, the repulsive force of dark energy will eventually become so strong that it will overcome all other forces in the universe. In the final moments of the cosmos, billions of years from now, the ever-increasing dark energy will first tear apart the great galaxy clusters. Then, it will unbind the galaxies themselves, flinging their stars into the void. As the end approaches, the force will become strong enough to overcome the gravity holding solar systems together, separating planets from their stars. Then, it will overcome the electromagnetic force, tearing the planets and stars themselves apart. In the final fraction of a second, it will overcome the strong nuclear force, ripping apart the atomic nuclei, reducing the entire universe to a shower of fundamental particles, each isolated from the others in an infinitely expanding void. The very fabric of space-time would be torn asunder. Webb's precise measurements of the expansion history of the universe are crucial to distinguishing between these scenarios. By looking at distant supernovae and the distribution of galaxies over cosmic time, it can help us determine the equation of state of dark energy, a parameter that tells us how its pressure relates to its density. If this parameter is exactly -1, it points to a cosmological constant and a big freeze. If it is less than -1, it points to phantom energy and a big rip. While current data is still consistent with a cosmological constant, the hints of a faster expansion keep the door open for these more exotic and more terrifying possibilities. There are other, less talked about scenarios as well. The Big Slurp, for instance, arises from the idea that our universe's vacuum state is not truly stable, but only metastable. It is like a ball resting in a small divot on the side of a large hill. It is stable for now, but a sufficient jolt could send it rolling down to a much lower true vacuum state. If a bubble of this true vacuum were to nucleate somewhere in the universe, it would expand at the speed of light, converting our universe into this new state as it went. The laws of physics, the fundamental constants, the very particles that make up our existence, would all be different inside this bubble. It would be the ultimate phase transition, and we would not see it coming. Our end would be instantaneous and absolute. Webb contributes to this line of inquiry by studying the most energetic events in the universe, searching for any sign of physics that deviates from our standard model, any hint that the vacuum of space-time is not as stable as we assume. The end of the universe is no longer a topic confined to theology or philosophy. It is a field of active, data-driven scientific research. The images Webb captures are not just snapshots of the past. They are frames in a cosmic movie. And by studying them carefully, we are beginning to glimpse the final scene. It is a profoundly human endeavor to seek to understand not just our origins, but our ultimate destiny. And Webb is our most powerful tool in this existential quest. The invisible components of the cosmos, dark matter and dark energy, do not just dictate its ultimate fate, they are the architects of its present tensed structure. Dark matter, comprising roughly 85% of the matter in the universe, is the silent, unseen majority. It does not emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, we know it is there. We see its gravitational influence everywhere we look. We see it in the rotation curves of galaxies, where the outer stars are moving far too fast to be held in orbit by the visible matter alone. We see it in the gravitational lensing of distant light, where the gravity of massive galaxy clusters, far greater than their visible mass could account for, bends and distorts the light from objects behind them, acting like a cosmic magnifying glass. And we see it in the large-scale structure of the universe, the cosmic web of filaments and voids, which could not have formed without the gravitational scaffolding of dark matter. Webb is revolutionizing the study of dark matter by providing the most detailed and precise maps of its distribution ever created, by meticulously analyzing the distorted shapes of thousands of background galaxies in its deep field images, a technique called weak gravitational lensing. Astronomers can reconstruct the invisible mass distribution of the foreground clusters. These new maps are revealing a picture of dark matter that is both beautifully consistent with our models and subtly challenging. On the one hand, they confirm that dark matter is distributed in vast, extended halos around galaxies and clusters, providing the gravitational glue that holds them together. But on the other hand, the cores of some of these dark matter halos appear to be less dense, or cuspier, than our simplest cold dark matter simulations predict. The CDM model assumes that dark matter particles are slow-moving and interact only through gravity. This discrepancy could be a sign that dark matter is more complex than we thought. Perhaps it is not cold, but warm, meaning the particles had higher velocities in the early universe, which would smooth out the density cusps in the centers of halos. Or, more intriguingly, perhaps dark matter interacts with itself through some unknown force, a dark force that operates only in the dark sector. These self-interactions could cause the dark matter particles to scatter off each other, effectively heating up the core of the halo and reducing its density. Webb's data is providing crucial ammunition for these debates. Furthermore, by observing the aftermath of galaxy cluster collisions, like the famous bullet cluster, Webb can study how dark matter behaves under extreme conditions. In these collisions, the hot gas of the two clusters crashes together and slows down, while the stars and the dark matter, interacting only weakly, pass right through each other. Webb's ability to map both the hot gas and the dark matter allows for a precise test of the self-interaction cross-section of dark matter. So far, dark matter appears to be remarkably collisionless, which puts tight constraints on many of the more exotic self-interacting models. The quest to identify the dark matter particle is one of the great unfinished revolutions in physics. It is a puzzle that connects the largest structures in the universe with the world of particle physics. While Webb cannot detect the dark matter particle directly, its detailed observations of the universe's structure are providing crucial, indirect clues that will guide the design of the next generation of particle detectors here on Earth. By studying the grand architecture of the cosmos, Webb is helping us to close in on the identity of its invisible architect. It is a testament to the power of astronomy that by looking out at the vastness of space, we can learn something fundamental about the subatomic world. Just as Webb is refining our understanding of the cosmic structure, it is also forcing us to reconsider the very process of creation within that structure, the formation of planets. The classic model of planet formation, the core accretion model, is a story of patient, steady growth. It begins with a young star surrounded by a protoplanetary disk, a spinning platter of gas and dust. Within this disk, tiny dust grains, coated in ice, begin to stick together. Through electrostatic forces, they form larger and larger aggregates, growing from pebbles to rocks, from rocks to boulders, and from boulders to planetesimals, kilometer-sized bodies that are the building blocks of planets. These planetesimals then continue to grow through gravitational encounters, their gravity pulling in more and more material, eventually forming the solid cores of planets. For gas giants like Jupiter, this core must grow to about 10 Earth masses quickly enough to gravitationally capture a massive atmosphere from the surrounding gas disk before the disk dissipates. A process that takes a few million years. It is a neat, orderly, and slow process. Webb's observations of protoplanetary disks, however, are painting a much more chaotic, dynamic, and complex picture. Its infrared vision can pierce through the obscuring dust and see the intricate structures within these planetary nurseries with unprecedented detail. It has revealed disks that are not smooth, continuous platters, but are carved with gaps, rings, and spiral arms. These structures are thought to be the signposts of forming planets, their gravity clearing out paths in the disk as they orbit the star. But the complexity and sharpness of these structures are challenging our models. Some gaps are too wide, some rings too narrow, to be explained by a single, peacefully accreting planet. This suggests that multiple planets may be forming in close proximity, their gravitational interactions creating a much more dynamic and turbulent environment. Moreover, Webb has discovered that the chemistry within these disks is far richer and more complex than we ever imagined. It has detected a zoo of complex organic molecules, including the building blocks of alcohols, aldehydes, and even simple sugars, frozen onto the surfaces of dust grains. This means that the raw ingredients for life are not just present, but abundant in the very places where new Earth-like planets are being born. This has profound implications for the theory of panspermia, the idea that life on Earth may have been seeded by organic material delivered by comets and asteroids that formed in our own solar system's protoplanetary disk. Webb's data suggests that this is not just a possibility, but a probability. But Webb has also uncovered a potential roadblock to this creative process. It has observed that the intense radiation from some young, active stars can create a hostile environment in the inner regions of their protoplanetary disks. This high-energy radiation can photoevaporate the gas, effectively blowing away the raw material needed for planet formation. It has also detected incredibly strong magnetic fields, threaded through these disks, which can create dead zones where turbulence is suppressed, preventing dust grains from clumping together. This suggests that planet formation is a far more precarious process than we thought, a delicate balance between the creative forces of gravity and chemistry and the destructive forces of stellar radiation and magnetic fields. The universe may be teeming with the ingredients for planets, but the ovens in which they are baked are not all set to the right temperature. This finding could help explain why, despite the vast number of stars, potentially habitable planets may still be rare. Webb is transforming planet formation from a story of slow, steady accumulation into a dramatic tale of cosmic weather, chemical complexity, and a constant battle between creation and destruction. It is showing us that the birth of a world like ours is not an inevitability, but the result of a precise and fortunate set of circumstances, a cosmic lottery that we were lucky enough to win. The cosmic lottery extends not just to the formation of planets, but to the very potential for life to take root and flourish upon them. Webb's unparalleled ability to analyze the atmospheres of exoplanets is ushering in a new era of comparative planetology, one where we can begin to understand the full diversity of worlds that the universe has to offer. And in this diversity, we are finding hints that the conditions for life may be both more widespread and more challenging than we had imagined. The discovery of potential biosignatures, like the combination of oxygen and methane on a nearby exoplanet, has rightfully captured the public's imagination. But Webb is also finding worlds that defy our expectations and challenge our definitions of habitability. It has studied Hycean worlds, a new class of planet that is larger than Earth but smaller than Neptune, with a deep global ocean covered by a thick hydrogen-rich atmosphere. Theoretically, life could exist in these oceans, but it would be a very different kind of life, adapted to high pressures and an environment devoid of a rocky surface. Webb's initial observations of these worlds have detected water vapor, but also hints of molecules like dimethyl sulfide, which on Earth is produced almost exclusively by marine phytoplankton. This is an incredibly tantalizing, though highly preliminary, clue that these exotic water worlds might harbor vast, hidden biospheres. At the same time, Webb has also provided cautionary tales. It has studied the atmospheres of planets orbiting red dwarf stars, the most common type of star in the galaxy. For a long time, these stars were considered prime targets in the search for life, as their long lifespans and stable energy output would seem to provide a perfect environment for life to evolve. However, Webb has revealed that many planets orbiting close to these stars, in their habitable zones, have been stripped of their atmospheres. Young red dwarfs are notoriously active, unleashing powerful stellar flares and intense ultraviolet radiation that can erode a planet's atmosphere over time, leaving it a barren, airless rock. This suggests that the habitable zone is not just about temperature, it is about the complex interplay between a planet's magnetic field, its atmospheric composition, and the violent nature of its host star. The universe may be full of planets in the right place, but many of them may have been sterilized by their own suns. Webb is also revolutionizing our understanding of our own solar system's history by studying the composition of asteroids and comets. It has confirmed the presence of complex organic molecules, including amino acids, on asteroids, lending strong support to the idea that the building blocks of life were delivered to the early Earth from space. By analyzing the isotopic ratios of water in comets, it is helping us to trace the origin of Earth's oceans. These observations are blurring the line between geology, chemistry, and biology, showing us that the story of life on Earth is inextricably linked to the history of the cosmos. The emergence of life is not a separate event, but a continuation of the same cosmic processes that form stars and planets. It is a story of cosmic chemistry, of stellar evolution, of galactic dynamics. And as Webb continues to collect these chemical fingerprints from distant worlds, it is compiling the first ever galactic census of habitability. It is a monumental task, and one that may not yield a definitive answer in our lifetimes. But for the first time, we have the tool to conduct the search in a systematic, scientific way. We are moving beyond speculation and into the realm of data. We are no longer just asking, are we alone? We are gathering the evidence that will one day provide the answer. It is a quest that is as much about understanding the universe as it is about understanding ourselves. For in the search for life elsewhere, we are forced to confront the very definition of life, the conditions that make it possible, and the profound and perhaps unique circumstances that led to our own existence. The universe as revealed by the James Webb Space Telescope is not only a place of unexpected creation and complex chemistry, but also of raw, untamed violence. The serene, clockwork cosmos of Newton has been replaced by a dynamic and often ferocious reality, where cosmic cataclysms are not rare exceptions, but fundamental drivers of cosmic evolution. Webb's infrared eyes have given us an unprecedented, ringside seat to some of the most energetic events in the universe. And these observations are challenging our understanding of stellar life cycles, galactic dynamics, and the very limits of physical law. For instance, The telescope has captured images of massive star collisions with a clarity that is both beautiful and terrifying. When two stars in a binary system spiral into each other and merge, the resulting explosion, known as a luminous red nova, can temporarily outshine an entire galaxy. Webb's observations have shown that these events are not just about the release of energy, they are powerful chemical factories. The shock waves from the collision create extreme temperatures and pressures, forging a host of heavy elements and flinging them out into the interstellar medium. But what has truly surprised astronomers is the sheer frequency and diversity of these stellar mergers. They appear to happen more often than our models predicted, suggesting that close binary star systems are more common, or their orbital decay is more rapid than we previously thought. This has significant implications for our understanding of gravitational waves, as merging neutron stars and black holes, the compact remnants of massive stars, are the primary sources for detectors like LIGO and Virgo. Webb's ability to identify the host galaxies of these mergers and study the aftermath of the explosion provides a crucial counterpart to the gravitational wave data, allowing for a much richer, multi-messenger understanding of these extreme events. But it's not just the violence between stars that Webb is uncovering, it's the violence within them. The telescope has observed unexpected, massive explosions on the surfaces of stars that were thought to be in stable phases of their life. These are not the final death throes of a supernova, but powerful eruptions on otherwise ordinary stars, some of them relatively close to Earth. These events, akin to solar flares but thousands of times more powerful, release vast amounts of energy and high-energy particles into their surrounding systems. The cause of these superflares is still being debated, but it likely involves the complex twisting and snapping of magnetic field lines in the star's atmosphere. The fact that they are occurring on stars not previously considered to be so active has become a cause for concern. It suggests that the space weather around other star systems could be far more extreme and unpredictable than we had assumed. This has direct implications for the habitability of exoplanets, a planet orbiting a star prone to such superflares, even if it is in the habitable zone, would be repeatedly bathed in lethal radiation, its atmosphere stripped away, and its surface sterilized. The search for life, therefore, must now include a search for stellar tranquility. A quiet sun may be just as important as a watery world. This new understanding of stellar violence is forcing a re-evaluation of cosmic risk. While the chances of a nearby star unleashing a superflare powerful enough to directly impact Earth are incredibly low, they are not zero. Webb's observations serve as a stark reminder that we live in a dynamic, and sometimes dangerous, cosmic neighborhood. The universe is not a benign and peaceful place. It is a stage for a constant drama of creation and destruction, and we are just beginning to appreciate the full scale of its power. The drama of cosmic violence reaches its zenith in the heart of galaxies, where supermassive black holes reign, these gravitational monstrosities, with masses millions or even billions of times that of our Sun, were once thought of as passive eaters, silently swallowing any matter that strayed too close. Webb has shown this picture to be woefully incomplete. Its observations of galactic centers have revealed them to be regions of astonishing and chaotic activity, cosmic storms of unparalleled intensity. The supermassive black hole at the center of our own Milky Way, Sagittarius A, was long thought to be relatively quiescent, but Webb has detected flares and outflows of hot gas from its immediate vicinity, suggesting that it is not dormant, but merely napping, periodically waking to feed on nearby stars and gas clouds. When this material spirals into the black hole, it forms an accretion disk, a swirling vortex of matter heated to millions of degrees, which glows intensely in the infrared. But not all of this matter is consumed. Powerful magnetic fields, generated by the spinning black hole and the accretion disk, can launch a portion of this material outwards in highly collimated jets that travel at nearly the speed of light. These jets can extend for thousands of light years, plowing through the host galaxy and carving out vast cavities in the interstellar medium. This process, known as galactic feedback, is now understood to be one of the most important mechanisms in regulating the growth of galaxies. The energy and radiation pumped out by an active black hole can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars. This effectively quenches star formation in the galactic core, and can even halt the growth of the galaxy as a whole. Webb has observed this process in action in distant galaxies. imaging the vast outflows of molecular gas being driven out of galactic centers by the power of their central black holes. It has shown that black holes are not just sinks of matter, they are cosmic engines, powerful thermostats that dictate the fate of their entire host galaxy. This discovery helps to solve a long-standing puzzle in astronomy. Why are the most massive galaxies not even bigger? Our models of hierarchical formation predicted that galaxies should just keep growing as they merge with others. But what we observe is that the most massive galaxies seem to have stopped forming stars billions of years ago. Galactic feedback from their supermassive black holes provides the perfect explanation. Once the black hole grows large enough, it effectively sterilizes its host galaxy, preventing any further growth. This intimate, and often violent, coevolution of black holes and galaxies is a new and exciting frontier in astrophysics, and Webb is providing the key data to unlock its secrets. By studying the relationship between the mass of a black hole and the properties of its host galaxy across cosmic time, we can begin to piece together the history of this cosmic dance, a dance that has shaped the very structure and appearance of the universe we see today. The centers of galaxies are not places of quiet solitude, they are the thundering hearts of the cosmos, where the most extreme forces of nature are at play, shaping the destinies of trillions of stars and worlds. Beyond the chaos of galactic cores and stellar explosions, Webb has also turned its gaze to the vast, seemingly empty chasms of the universe, the great cosmic voids. These are the largest and most underdense regions of the cosmos, vast deserts of space-time containing almost no galaxies, stars, or gas. In the standard picture of the cosmic web, these voids are the natural consequence of gravity. As matter clumps together to form filaments and clusters, it leaves behind these vast empty regions. They were thought to be simple, boring, and largely devoid of interest. Webb, however, has revealed that even the emptiness is not what it seems. During its deep space observations, the telescope has discovered an incredibly large cosmic void, a region of space hundreds of millions of light years across that is even emptier than our models predicted. The sheer scale and emptiness of this void are difficult to explain. It is as if a giant cosmic bubble was inflated in the early universe, pushing all the matter to its edges. One possible explanation is that this void is the result of a particularly large negative density fluctuation in the primordial universe, a region that started out with slightly less matter than average and has been growing ever since, as its weak gravity has been unable to compete with the overall expansion of the universe. But the scale of this void hints at something more. Some cosmologists have speculated that such voids could be the imprint of another universe bumping into ours in the context of the multiverse. In some versions of eternal inflation, our universe is just one bubble in a vast, eternally inflating space-time, and collisions between these bubble universes are possible. Such a collision would leave a bruise on our CMB, a circular cold spot, and could trigger a large-scale outflow of matter, creating a vast void. While highly speculative, the existence of such a giant void provides a potential, albeit circumstantial, piece of evidence for this extraordinary idea. But even within the voids, Webb has found unexpected surprises in what were thought to be the darkest, most desolate regions of space. Webb has discovered faint, isolated objects, shining where nothing should be shining. These are not normal stars or galaxies. Their light signatures, their spectra, do not match any known celestial object. They are too small and too isolated to be dwarf galaxies, and too bright to be single stars. Their nature is a complete mystery. Could they be a new type of object? Perhaps primordial black holes formed in the first second of the universe's existence, surrounded by a faint halo of captured gas that is slowly accreting onto them? Or could they be evidence of a more exotic form of matter? Perhaps dark stars powered not by nuclear fusion, but by the annihilation of dark matter particles in their cores. The existence of these void objects challenges our understanding of structure formation. It suggests that even in the most underdense regions of the universe, pockets of matter can collapse and form luminous objects, a process our current simulations struggle to reproduce. The voids are no longer the boring, empty parts of the cosmic map. They are a new frontier for discovery, a laboratory for testing our understanding of gravity, dark matter, and the very initial conditions of the universe. They are a reminder that the universe is full of secrets, not just in the bright, crowded hearts of galaxies, but also in its darkest, most solitary corners. The emptiness speaks, and Webb is the first to truly hear its voice. The universe's inventory of the strange and the new is not limited to its largest structures or most violent events. It extends down to the very building blocks of matter and the forces that govern them. Webb's high-precision measurements are probing the universe with a sensitivity that allows us to test the fundamental laws of physics in ways that are impossible in terrestrial laboratories. And in these tests, we are beginning to see faint, but persistent, hints of new physics beyond our standard model. One of the most intriguing of these is the detection of the strongest magnetic field ever observed in the universe. This field, millions of times stronger than anything we can generate on Earth, was found surrounding a magnetar, a type of neutron star with an incredibly powerful magnetic field. But the field observed by Webb extends over a much larger region of space than the neutron star itself, suggesting a more complex and previously unknown structure. The sheer strength of this field is pushing the limits of our understanding of magnetohydrodynamics, the physics of electrically conducting fluids. How such a field is generated and sustained is a major puzzle. It may be a remnant of the magnetic field of the progenitor star, amplified to an incredible degree during the collapse of its core in a supernova, or it may be generated by a dynamo mechanism within the rapidly spinning neutron star, a process that is still not fully understood. The existence of such an extreme magnetic field has profound implications. These fields can influence the paths of high-energy cosmic rays. They can affect the process of star formation in their vicinity, and they can even, in theory, cause the vacuum of space itself to become birefringent, meaning it would affect the polarization of light passing through it, a prediction of quantum electrodynamics that has yet to be observed. Webb's discovery provides a new laboratory for studying physics under the most extreme conditions imaginable, conditions that we can never hope to replicate on Earth. But Webb's search for new physics is not just about finding the extreme, it is also about finding the subtle. The telescope's precise measurements of the chemical composition of the oldest stars in the universe are providing a crucial test of Big Bang nucleosynthesis, the theory that predicts the primordial abundances of the light elements like hydrogen, helium, and lithium. While the theory has been remarkably successful, there has been a long-standing lithium problem. The observed abundance of lithium in old stars is about 3 times lower than the theory predicts. Webb's ability to get clean, high-resolution spectra of these ancient stars is helping to clarify this issue. It is possible that the discrepancy is not a flaw in the Big Bang theory, but is due to stellar processes that destroy lithium in the outer layers of these stars over their long lifetimes. By studying stars of different ages and temperatures, Webb can help to disentangle the primordial abundance from the effects of stellar evolution. However, if the discrepancy persists, even after accounting for these effects, it could be a sign of new physics in the early universe, perhaps related to the decay of a new particle or a modification to the laws of thermodynamics at high temperatures. These are subtle, painstaking measurements, far from the headline-grabbing images of beautiful nebulae, but they are at the heart of Webb's scientific mission. It is in these subtle deviations from our expectations, these small cracks in the facade of our standard models, that the seeds of the next revolution in physics are often found. The universe is a vast and complex place, and it is through the combined power of observing the grand and measuring the minute that we can hope to piece together its deepest secrets. The tapestry of cosmic discovery being woven by Webb is not just composed of threads of light and gravity, but also of the complex, life-giving molecules that drift in the spaces between the stars. The telescope has revolutionized the field of cosmic chemistry, revealing that the interstellar medium is a far richer and more complex chemical laboratory than we ever knew. Its infrared spectrographs can identify the telltale absorption and emission lines of specific molecules with incredible sensitivity, allowing us to take a chemical inventory of the universe. And that inventory has been full of surprises. Webb has confirmed the widespread presence of polycyclic aromatic hydrocarbons, complex carbon-based molecules that on Earth are often associated with the byproducts of combustion, like soot. In space, however, they are thought to form in the cool, carbon-rich atmospheres of dying stars and are then spread throughout the galaxy. These molecules are incredibly important, as they are thought to play a crucial role in the heating and cooling of the interstellar medium, and may even act as catalysts for the formation of more complex molecules. But what has been truly astonishing is the sheer variety and complexity of the organic molecules that Webb is finding. In the dense, cold molecular clouds where new stars and planets are born, Webb has detected the signatures of not just simple molecules like water and carbon monoxide, but also more complex species like methanol, ethanol, and acetic acid, the main component of vinegar. These are not just random molecules, they are the building blocks of the more complex organic chemistry that leads to amino acids, sugars, and the other components of life. The fact that they are forming in these cold, dark clouds, even before the birth of a star, suggests that the universe has a natural tendency towards chemical complexity. The process is thought to begin with simple molecules freezing onto the surfaces of tiny dust grains, forming an icy mantle. Within this ice, the faint ultraviolet light from distant stars can trigger a series of chemical reactions, breaking apart the simple molecules and allowing them to recombine into more complex forms. Over millions of years, this slow, cold chemistry builds up a rich inventory of organic material. When a new star and protoplanetary disk form from the collapse of this cloud, this organically rich material is incorporated into the comets and asteroids that will eventually deliver it to the young planets. Webb's observations have provided the most direct evidence yet for this entire process. It has imaged the icy mantles on dust grains. It has identified the complex organic molecules within those ices, and it has detected the same molecules in the inner regions of protoplanetary disks, right where new Earths are forming. It is a beautiful, coherent story that connects the chemistry of the interstellar medium directly to the origins of life. The universe, it seems, is not just littered with the ingredients for life, it has a well-established supply chain for delivering them. This has profound implications for our understanding of our own origins. It suggests that the emergence of life on Earth was not a fluke, a 1 in a trillion chemical accident, but was perhaps the natural, and maybe even inevitable, outcome of a universal process of chemical evolution. This perspective, known as cosmic gradualism, shifts the focus from a single, miraculous spark of life to a long, continuous chain of events, stretching from the cold hearts of molecular clouds to the warm oceans of young planets. We are not just star stuff. As Carl Sagan famously said, we are the product of a cosmic chemistry that has been unfolding for billions of years, a chemistry that Webb is now allowing us to witness in its full glory for the very first time. The universe that the James Webb Space Telescope is unveiling is not just a physical space of stars and galaxies, it is also a philosophical landscape that forces us to confront our most fundamental assumptions about reality, existence, and our own place in the cosmos. Every image, every data point, is not just a piece of a scientific puzzle, but also a mirror reflecting our own curiosity, our own finitude, and our own search for meaning. The discovery of galaxies that are older and more mature than our theories predicted does not just challenge our models of cosmology, it challenges our sense of temporal progression and our place within it. We have a natural human tendency to see our own time, our own planet, our own galaxy as somehow special, as the culmination of a long evolutionary process. But Webb's data suggests that the universe was capable of creating complexity and order much earlier than we thought. Our Milky Way is not the venerable elder we imagined, but perhaps just one of many, a late bloomer in a cosmos that was already teeming with grand galactic structures. This is a profound lesson in cosmic humility. It decenters humanity not just from the center of the solar system, as Copernicus did, or from the center of the galaxy, as Shapley did, but from a privileged position in cosmic time itself. We are not the pinnacle of cosmic evolution. We are an eddy in a river that has been flowing for a long, long time, a river that has seen other, perhaps grander, civilizations rise and fall before our sun was even born. This realization can be both unsettling and liberating. It is unsettling because it removes any sense of cosmic specialness, any notion that the universe was somehow designed with us in mind, but it is liberating because it opens up the vast expanse of cosmic history to the possibility of others. The universe is not a story that leads only to us. It is a grand, sprawling epic with countless protagonists, and we have only just begun to read its opening chapters. This perspective forces us to think on truly geological and even cosmological timescales. The challenges we face as a species, climate change, political conflict, resource depletion, can seem insurmountable on a human timescale, but when viewed against the backdrop of a universe that is at least 13.8 billion years old, and perhaps much older, our problems, and indeed our entire existence, are but a fleeting moment. This does not mean they are insignificant. On the contrary, it highlights the incredible preciousness and fragility of this conscious moment we have been given. The universe has been here for an immense amount of time, and will likely be here for an immense amount of time to come. The question is, will we Webb's images are a silent, powerful call to a longer-term perspective? A perspective that transcends national borders, political ideologies, and even the lifespan of our species. They invite us to see ourselves as part of a much larger, much older story, and to act with the wisdom and foresight that such a perspective demands. The philosophical implications deepen when we consider the search for extraterrestrial life, a search that Webb has transformed from a speculative exercise into a data-driven science. The detection of potential biosignatures in the atmosphere of a nearby exoplanet is a scientific milestone, but it is also a philosophical bombshell waiting to explode. The confirmation of life beyond Earth, even microbial life, would be the most profound discovery in the history of science, a discovery that would fundamentally reshape our understanding of ourselves and our place in the universe. For millennia, humanity has looked up at the stars and asked, "Are we alone?" This question is at the heart of our religions, our mythologies, and our scientific inquiries. It is a question about uniqueness, about purpose, and about our ultimate cosmic significance. To find that the answer is no, that life is not a unique miracle confined to our own small world, would be to complete the Copernican revolution. It would be the final step in the long, and often painful, process of removing humanity from the center of creation. But what would the discovery of life, particularly intelligent life, actually mean for us? On the one hand, it could be a source of immense hope and inspiration. The knowledge that we are not alone, that consciousness is a phenomenon that has arisen independently elsewhere, would provide a powerful sense of connection to the cosmos. It would suggest that the universe is not a sterile, meaningless void, but is, in some fundamental way, life-friendly, even consciousness-friendly. It could also provide a powerful impetus for global unity. The realization that we are all Earthlings, members of one of many cosmic civilizations, could help to dissolve the petty national and cultural divisions that have plagued our history. The overview effect experienced by astronauts, a profound cognitive shift in awareness that comes from seeing the Earth as a fragile, unified whole floating in the void, could become a shared experience for all of humanity. On the other hand, the discovery of intelligent life could also be a source of profound existential dread. The Fermi paradox. The apparent contradiction between the high probability of extraterrestrial life and the lack of any evidence for it has long haunted our search. One possible solution to the paradox is the Great Filter, a hypothetical evolutionary or technological hurdle that is so difficult to overcome that it prevents almost all civilizations from reaching a stage where they can communicate or travel between the stars. The filter could be behind us or it could be ahead of us. If we were to detect the ruins of a long-dead alien civilization, it would be a chilling discovery. It would suggest that the Great Filter is still in our future, a silent warning that our own technological prowess may be the instrument of our own doom. Webb's observations, while not yet capable of detecting alien artifacts, are providing the first statistical data on the prevalence of potentially habitable worlds. This data will help us to better constrain the variables in the Drake equation, the famous probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Every new Earth-like planet discovered increases the probability of life, but it also deepens the mystery of the Great Silence. We are living in a unique moment in history, a moment where a question that was once the sole domain of philosophers and priests is now being addressed with the rigorous tools of science. The answer, whatever it may be, will have a profound and lasting impact on the future of human thought. The universe that Webb is revealing is not just challenging our place in time and our uniqueness in the cosmos, it is also challenging our very understanding of reality itself through its observations of the invisible. The confirmation of the existence and distribution of dark matter and dark energy is not just a triumph of observational cosmology, it is a profound statement about the limits of human perception and the nature of knowledge. We have discovered that 95% of the universe is made of stuff that we cannot see, cannot touch, and cannot directly interact with. Our entire reality, everything we have ever known, the stars, the planets, ourselves, is just 5% of the cosmic inventory. We are the foam on the surface of a vast, dark ocean. This is a philosophical realization as much as a scientific one. It teaches us that the reality accessible to our senses is not the whole of reality. It is a powerful argument against a naive empiricism, the idea that what is real is only what can be directly observed. The existence of dark matter and dark energy was not discovered by seeing them. It was inferred through their effects on the things we can see. It is a triumph of reason, of our ability to build models, make predictions, and test them against the world. It shows that the human mind, through the language of mathematics and the process of science, can grasp realities that are forever beyond the reach of our biological senses. But this discovery also brings with it a deep sense of epistemological humility. It reminds us that our understanding of the universe is, and perhaps always will be, incomplete. If we were wrong about 95% of the universe's composition for most of our history, what else are we wrong about? What other fundamental components of reality are we currently blind to? The search for the nature of dark matter and dark energy is not just a scientific quest. It is a quest to understand the true substance of the world we inhabit. It forces us to confront the possibility that the universe is not just stranger than we imagine, but stranger than we can imagine. The very language and concepts we use to describe the world may be inadequate to the task of capturing its ultimate nature. Perhaps dark matter is not a particle in the traditional sense, but a manifestation of a higher dimensional reality, its gravitational influence leaking into our three dimensions of space. Perhaps dark energy is not an energy of the vacuum, but a sign that our understanding of gravity itself is flawed, a hint that the laws of physics are not constant, but are evolving along with the universe. These are speculative ideas, but they are the kind of ideas that are born in times of scientific crisis. When the data refuses to fit our established models, Webb is providing the data that is fueling this crisis. And in doing so, it is pushing us towards a new, and perhaps more profound, understanding of the cosmos. The discovery of the dark universe is not just about adding new items to our cosmic inventory. It is about fundamentally changing our relationship with reality, forcing us to accept our limitations and to embrace the deep and enduring mystery that lies at the heart of existence. This sense of mystery is amplified by the anomalies, the outliers, the observations that simply do not fit, the discovery of a massive cosmic wall, the detection of mysterious light signals, the observation of objects moving at incredible speeds. These are not just interesting astronomical curiosities, they are potential cracks in our edifice of knowledge, through which the light of a new understanding may be dawning. The cosmic wall, for example, is not just a challenge to the cosmological principle. It is a challenge to our understanding of causality and information in the early universe. How could a structure so large have formed? The speed of light imposes a fundamental limit on how quickly information and influence can travel. In the early universe, regions of space that are now billions of light years apart were not in causal contact with each other. They should have evolved independently. Yet, the existence of such a coherent, large-scale structure suggests that there may have been some form of superluminal connection or preordained correlation in the primordial universe. This is the same problem that the theory of cosmic inflation was invented to solve, the horizon problem, and the cosmic wall may be telling us that our current theory of inflation is not the whole story. Similarly, the mysterious light signals, whether they prove to be natural or artificial, force us to confront the unknown. If they are natural, they represent a new type of astrophysical object or process, a new piece of the cosmic puzzle that will enrich our understanding of the universe's physics. If they are artificial, they represent something far more profound, the existence of another technological intelligence. This would raise a host of new philosophical and ethical questions. Should we respond? What would we say? How would the knowledge of their existence change our society, our religions, our sense of self? The search for extraterrestrial intelligence has often been on the fringes of mainstream science, but Webb's ability to detect atmospheric biosignatures and its potential to stumble upon anomalous signals is bringing it back into the heart of scientific inquiry. These anomalies are crucial to the progress of science. Science does not advance by only confirming what we already know. It advances by confronting what we do not know, by grappling with the data that does not fit. It is in the patient, rigorous, and open-minded investigation of these anomalies that the next great breakthroughs will be found. Webb is a powerful anomaly-generating machine. Its sensitivity and its unique observational window in the infrared are allowing it to see the universe in a new light, to uncover phenomena that were previously hidden from us. Each of these mysteries is an invitation, a call to adventure for the human mind. They are a reminder that the universe is not a closed book that we are close to finishing, but a vast, open library with an infinite number of volumes, most of which we have not even opened yet. The true value of an instrument like Webb is not just in the answers it provides, but in the new, deeper, and more profound questions it allows us to ask. It is a tool for expanding not just our knowledge, but our sense of wonder. The ultimate philosophical question that Webb's observations raise is about our own future, both as a species and as a part of a cosmic story. The telescope's data on the accelerating expansion of the universe and the potential for a big rip ending forces us to confront our own cosmic mortality. The idea that the universe itself has a finite, and potentially violent, end can be a source of existential angst. What is the meaning of our endeavors, our art, our science? If it is all destined to be torn apart in a cosmic cataclysm, this is not a new question. Philosophers and theologians have grappled with the problem of meaning in the face of mortality for centuries. But Webb is bringing this question into the realm of empirical science. We may, for the first time in history, be able to make a data-driven prediction about the ultimate fate of our reality. But this knowledge does not have to lead to despair. On the contrary, it can be a powerful source of meaning and purpose. The philosopher Bertrand Russell, in his essay A Free Man's Worship, argued that it is precisely in the face of a godless, indifferent, and ultimately doomed universe that humanity can find its true dignity. We must, he wrote, build our lives on the firm foundation of unyielding despair. But from that despair, we can create our own meaning, our own values, our own beauty. Webb's vision of a potentially finite universe can be seen in a similar light. The knowledge that our cosmic moment is fleeting can imbue it with a profound sense of preciousness. It can motivate us to make the most of the time we have, to cherish our planet, to foster compassion, and to pursue knowledge and beauty for their own sake, not for some eternal reward, but for the simple, profound value they have in the here and now. Furthermore, the hints of new physics, the anomalies in space-time, the potential for a deeper understanding of gravity, these also offer a glimmer of a different kind of hope. While still in the realm of extreme speculation, the idea that humanity could one day understand the laws of physics well enough to manipulate space-time, to travel between the stars, or even to survive the end of our own universe, is a powerful and enduring dream. Webb's discovery of potential space-time anomalies or natural tunnels is a long, long way from a warp drive, but it is a scientific data point that touches on this dream. It suggests that the universe may contain secrets and possibilities that could, in the far future, offer a path to a longer-term survival. This is not a prediction, it is an inspiration. It is a call to continue our quest for knowledge, not just to understand the universe, but perhaps one day to become active participants in its future. Webb's legacy, therefore, will not just be in the scientific papers it generates or the theories it rewrites. Its legacy will be in the way it shapes our collective human consciousness. It is a tool that allows us to see our origins, to contemplate our place in the cosmos, and to imagine our future. It is a source of humility, of wonder, and of a profound sense of connection to the vast and mysterious universe that has given us birth. In looking out, we are also looking in, and what we are finding is that the story of the cosmos is also, in the deepest sense, our own. The ongoing cascade of discoveries from the James Webb Space Telescope is not merely adding new chapters to our understanding of the cosmos, it is compelling us to fundamentally rethink the very processes of creation. From the birth of the first stars to the intricate assembly of planetary systems. We are moving from a static picture of cosmic evolution to a dynamic, and often violent, narrative where nothing is as simple as our previous models suggested. Webb's infrared vision has peeled back the dusty curtains of stellar nurseries, revealing the birth of stars in unprecedented detail. It has shown us that the process is not a gentle, uniform collapse of a gas cloud. Instead, It is a turbulent and chaotic affair, shaped by the complex interplay of gravity, magnetic fields, and powerful outflows of material from the young protostars themselves. These outflows, bipolar jets of gas traveling at hundreds of kilometers per second, are launched from the poles of the young star and plow into the surrounding molecular cloud, creating spectacular, glowing shockwaves. Webb has imaged these jets with stunning clarity, revealing intricate bow-shock structures and knots of heated gas. These observations are crucial because these outflows act as a form of stellar feedback, clearing away the surrounding material and ultimately limiting the final mass of the star. They are a key part of the self-regulation process that governs star formation across the galaxy. But Webb has also revealed a new puzzle. In some regions, it has observed that the formation of massive stars seems to be much more efficient than our theories predict. These stellar behemoths, tens or even hundreds of times the mass of our Sun, live short, spectacular lives and have a profound impact on their environment, their powerful winds and intense radiation shaping the entire galaxy. Understanding how they form is one of the key challenges in astrophysics. Webb's data suggests that they may not form in isolation, but in dense, competitive clusters, where multiple protostars vie for the same reservoir of gas, a process known as competitive accretion. It has also provided evidence for the merger of smaller protostars as a viable pathway to forming the most massive stars. This new, more dynamic picture of star birth is rewriting the textbooks, showing us that the creation of a star is not a solitary event, but a complex environmental process, a story of cosmic weather and celestial competition. This complexity extends to the final, dramatic moments of a star's life. The death of a star in a supernova explosion is one of the most powerful events in the universe, an explosion that can briefly outshine its entire host galaxy. For decades, our understanding of these events was based on relatively simple, one-dimensional models of a collapsing stellar core. Webb is showing us that this picture is far too simple. By observing the remnants of recent supernovae in nearby galaxies, the telescope is providing a three-dimensional archaeological look at the explosion itself. Its infrared spectrographs can map the distribution of different chemical elements within the expanding cloud of debris. These maps have revealed a surprising degree of asymmetry and clumpiness. The heavy elements forged in the heart of the star, like iron and silicon, are not expanding in a uniform sphere, but are ejected in clumpy, jet-like structures. This strongly suggests that the supernova explosion itself is not a spherically symmetric event, but is fundamentally asymmetric, perhaps driven by turbulent convection in the collapsing core or by the rapid rotation of the progenitor star. This has profound implications. The asymmetry of the explosion can impart a powerful kick to the neutron star or black hole that is left behind, sending it careening through the galaxy at hundreds of kilometers per second. Webb's observations of the positions of young pulsars relative to the center of their supernova remnants are providing crucial data to test these kick models. Furthermore, the clumpy distribution of elements means that the chemical enrichment of the interstellar medium is not a smooth, uniform process. Some regions of a galaxy may be preferentially enriched with certain heavy elements, which could in turn influence the composition of the next generation of stars and planets that form in that region. Webb has also provided us with the most detailed look yet at the prelude to these explosions. It has captured stars in their final, unstable throes, months or years before they go supernova. These observations have shown that many massive stars undergo violent, eruptive mass loss events right before they die, shedding their outer hydrogen envelopes. This pre-supernova activity was not predicted by standard stellar evolution models and suggests that the final stages of a star's life are far more dynamic and unstable than we thought. By studying these precursors, we may one day be able to predict supernova explosions before they happen, giving us the chance to observe the cataclysmic event itself from its very first moments. This would be a revolutionary achievement, providing an unprecedented window into the heart of one of nature's most extreme phenomena. From the turbulent birth of protostars to the asymmetric death of massive stars, Webb is painting a new, more vibrant, and more violent picture of the stellar life cycle. A picture that is crucial to understanding the grander story of cosmic evolution. The grand cosmic cycle of birth, life, and death is not just about stars, it is also about the planets that orbit them. And here, too, Webb is forcing a fundamental reevaluation of our theories. The telescope has provided us with the most detailed images ever taken of protoplanetary disks, the swirling platters of gas and dust where new worlds are born. These images have revealed a wealth of intricate structures, gaps, rings, spirals, and vortices that are the telltale signs of ongoing planet formation. But the complexity of these structures is challenging our models. For instance, Webb has observed multiple concentric gaps in some disks, suggesting the presence of several planets carving out their orbits. However, the planets required to create these gaps would need to be in specific, stable resonant orbits, a configuration that is not always easy to achieve in simulations. This has led to the development of new theories, such as the idea that a single, massive planet can open up multiple gaps through its complex gravitational interaction with the disk. Webb has also discovered that these disks are not just composed of gas and dust, they are threaded with powerful magnetic fields. These fields can channel the flow of gas onto the young star, a process known as magnetospheric accretion, and they can also launch powerful disk winds that carry material away from the disk. This magnetic activity plays a crucial role in the evolution of the disk, affecting its lifetime, its chemical composition, and ultimately, its ability to form planets. In some cases, strong magnetic fields can create dead zones in the disk, regions of low turbulence where dust grains struggle to grow, potentially inhibiting planet formation. But what has been perhaps most surprising is the discovery of what appears to be a common phenomenon that actively prevents planet formation. In a significant fraction of the protoplanetary disks observed by Webb, the intense ultraviolet and X-ray radiation from the central star is heating the gas in the disk, causing it to photoevaporate into space. This process can be so efficient that it can clear out the entire gas content of a disk in just a few million years, cutting short the time available for gas giant planets to form. This suggests that the formation of a Jupiter-like planet may be a race against time, a battle between the slow, patient process of core accretion and the rapid, destructive force of photoevaporation. This discovery has major implications for our understanding of the architecture of planetary systems. It may help to explain why solar systems like our own, with gas giants in the outer regions and smaller rocky planets in the inner regions, are relatively rare. In many systems, the gas giants may simply not have had time to form before the gas disk was blown away. This new, more precarious view of planet formation underscores the fortunate circumstances that led to the existence of our own solar system. It is a reminder that the creation of a stable, life-bearing planetary system is not a given, but the result of a complex and finely tuned cosmic dance. A dance that Webb is now allowing us to observe in all its intricate and often unforgiving beauty. The chemical story of the cosmos, from the first light elements forged in the Big Bang to the complex organic molecules that form the basis of life, is another area where Webb is making revolutionary discoveries. Its powerful infrared spectrographs are a kind of cosmic prism, capable of breaking down the faint light from distant objects into its constituent wavelengths, revealing the chemical fingerprints of the atoms and molecules present. This has allowed us to perform a chemical census of the universe with unprecedented detail and to trace the story of cosmic chemical evolution through time. One of Webb's most profound contributions in this area has been the study of the composition of the first stars. These population 3 stars, as they are known, are the true first generation of stars, formed from the pristine hydrogen and helium of the early universe. They have never been directly observed, as they were incredibly massive and short-lived, exploding as supernovae just a few million years after they formed, but we can search for their chemical legacy by analyzing the atmospheres of the oldest surviving stars in our own galaxy, population 2 stars. Webb can look for the unique chemical signature of the population 3 supernovae that enrich the gas clouds from which these later stars formed. Our models predict that the first stars should have exploded in a very specific way, producing a distinct pattern of heavy elements. Webb's initial observations have found stars with extremely low metallicity, the astronomical term for any element heavier than hydrogen and helium, but their detailed abundance patterns do not always match the predictions for a simple population 3 enrichment. This suggests that the first supernovae may have been more diverse than we thought, or that the early interstellar medium was not well mixed, leading to localized pockets of unusual chemical enrichment. This is a subtle but important puzzle, as the chemical yield of the first stars is what sets the stage for all subsequent cosmic evolution, including the formation of planets and the emergence of life. On the other end of the chemical spectrum, Webb is transforming our understanding of cosmic dust. These tiny submicron-sized particles of carbon and silicate are not just a nuisance that obscures our view of the distant universe, they are crucial players in cosmic chemistry. They provide the surfaces on which new molecules can form. They absorb starlight and re-radiate it in the infrared, and they are the fundamental building blocks of planets. Webb's detailed spectral analysis of cosmic dust clouds has revealed that their composition is far more complex and varied than we thought. It has confirmed the presence of complex silicates, similar to the sand on our beaches, but also more exotic materials like crystalline water ice, solid carbon dioxide, and a host of complex organic molecules. The discovery of these ices is particularly important, as they represent a major reservoir of the volatile elements necessary for life. Webb has shown that these ices are not just confined to the dense, dark hearts of molecular clouds, but are also present in the outer regions of protoplanetary disks, right where comets form. This provides a direct link between the chemistry of the interstellar medium and the composition of the comets and asteroids that are thought to have delivered water and organic material to the early Earth. Webb is, in essence, following the water trail. From the cold clouds between the stars to the potentially habitable worlds orbiting them, it is a story that connects the vastness of the cosmos to the origins of our own existence, a story that is being written, molecule by molecule, in the data that Webb sends back to Earth. The universe that Webb is revealing is not just a collection of objects and processes, it is a unified, interconnected system, where the largest scales are influenced by the smallest, and the distant past shapes the present. One of the most powerful ways to probe this interconnectedness is through the phenomenon of gravitational lensing, and Webb is the most powerful lensing telescope ever built. When the light from a distant galaxy passes by a massive object, like another galaxy or a cluster of galaxies, its path is bent by the gravity of the foreground object. This can distort the image of the background galaxy, stretching it into arcs and even creating multiple images of the same object. By studying these distortions, we can map the distribution of mass in the foreground lens, including the invisible dark matter, but Webb is taking this technique to a whole new level. Its incredible sensitivity allows it to detect the lensed images of some of the most distant galaxies ever seen, galaxies that would be far too faint to observe directly. These galaxy clusters act as natural cosmic telescopes, their immense gravity magnifying the light from the universe's dawn, allowing Webb to peer even deeper into the past than it could on its own. This technique has been instrumental in the discovery of some of the earliest and most distant galaxy candidates, pushing our observational frontier back to just a few 100 million years after the Big Bang. But gravitational lensing is not just a tool for finding distant objects, it is also a powerful probe of fundamental physics. According to Einstein's theory of general relativity, the amount of lensing depends only on the mass of the lensing object. However, some alternative theories of gravity predict that the lensing of light might be different from the gravitational pull on matter. Webb's ability to precisely map both the distribution of mass and the distribution of hot gas in galaxy clusters allows for a powerful test of these alternative theories. So far, Einstein's theory has passed every test with flying colors, but scientists are continuing to push the precision of these measurements, searching for any deviation that could signal new physics. Webb is also using a more subtle form of lensing, called microlensing, to search for isolated, wandering objects in our own galaxy. When a compact object, like a lone black hole or a free-floating planet, passes in front of a distant star, its gravity can briefly magnify the light of the background star, creating a characteristic brightening event. By monitoring millions of stars in the dense fields of the galactic bulge, Webb can detect these fleeting microlensing events. This is one of the only ways to detect these dark, isolated objects that would otherwise be completely invisible. This search is crucial to understanding the population of stellar remnants and rogue planets in our galaxy, objects that have been ejected from their home systems and now wander the darkness of interstellar space. The universe, through the elegant and precise language of gravitational lensing, is providing us with a tool to study its most massive structures, its most distant objects, and its darkest inhabitants. It is a beautiful example of how a single physical principle, the curvature of space-time by mass, can be used to unlock a vast range of cosmic secrets. Webb's mastery of this technique is not just providing stunning images of distorted galaxies, it is providing a new, sharper lens through which we can view the entire cosmos. From the dawn of time to the dark wanderers in our own galactic backyard,